Learn relational database design from the ground up in this comprehensive course. You'll learn about SQL fundamentals, entity relationship modeling, normalization, data types and constraints, and more. This course was created by Dr. Howe, who recently published a book on the topic from Manning Publications.
You are keeping track of 50 club members in a spreadsheet. It starts simple: name, email, and phone numbers. But then someone gets added twice. Someone else's email gets overwritten. Now you're trying to track payments, committees, event RSVPs, and it's chaos. That's when you realize you need structure. You need a better way to organize, connect, and protect your data. This is where databases come in. But what exactly is a database? Why do we organize data into tables? And what makes something a primary key? Why do all modern apps, from social media to your banks, rely on something called an RMDBS? In this video, we'll unpack the building blocks that makes it all work. We will start by defining a set of fundamental concepts before giving you the first taste of SQL, or SQL. We will start with a simple question. What are relational databases and tables? First, what is a relational database? A relational database is simply a collection of tables. So what's a table then? A table is something like a spreadsheet with data. As you already know, data in a spreadsheet is organized into rows and columns. The same can be said for a table. However, a table is different from a spreadsheet with data, because a table is used to represent an entity or a relationship between entities. So to fully understand what a table is, we need to understand what an entity is first. So what exactly is an entity? An entity is an object, or a concept, that can be described by many attributes. Suppose that we are running an online store that's called the Sci-Fi Collective, which sells the sci-fi products, such as time machines that take you back to only 5 minutes, in case you forget your keys. Products sold by the Sci-Fi Collective are entities, and each can be described by at least 4 attributes: the name, description, price, and manufacturer. When we map all the products to a table in the database supporting the online store of the Sci-Fi Collective, the 4 attributes will be mapped to 4 individual columns, and each product will be represented as a row in this table, like what you see here on the screen. In addition to the 4 columns, you may notice that we have added another column, Product ID, in the preceding table. All the values in the Product ID column are unique and can be used to identify an individual row. We call Product ID the primary key of the product table. Each table should have a single primary key. We will discuss more on primary keys in the future videos. That said, a table is similar to a spreadsheet with data, but also bears important differences because a single table is supposed to represent a single entity, or a single relationship between different entities. If you try to squeeze more than 1 entities together into a single table, bad things can happen. For example, if we decide to store the information of customers and products into 1 table for the Sci-Fi Collective store. For example, the table may look like this. This table is a typically poorly designed table. You can spot the data redundancy issues first, like this. Beyond that, such a design can cause many unexpected problems. For example, if a customer's information appears in only 1 row when we want to delete a product, we will have to delete the customer in the same row from our database. This problem is known as delete anomaly. For another example, from time to time, we need to insert into this table a product that no customers have bought yet. But the table requires us to provide valid customer information whenever we try to add a new row into this table. The contradicting requirements leave us in an awkward situation. we can't add any new products at all. This problem is known as the insertion anomaly. In short, a table can only represent a single entity, or a single relationship between different entities. Now, we have come to know quite a few important concepts. Let's move to the next. The Relational Database Management System, short for RDBMS. What's an RDBMS? First, an RDBMS is a software. It's responsible for interacting with the underlying hardware and operating system so that it can take care of how to physically store and manage data in relational databases. You may be familiar with some commonly used RDBMS, such as MySQL, MariaDB, or Postgres. When you need to deploy a database that you designed, you will need to interact with one of the available RDBMS on the market. So to link RDBMS back to the concepts of database and tables, an RDBMS is used to manage and maintain different databases. A database organizes data into different tables. Another important purpose an RDBMS serves is to provide tools and functions to manage databases. One of the most notable tools that nearly all RDBMS supports is the Structured Query Language, short for SQL, or the SQL, a programming language that you can use to create, modify, and query data stored in tables. Although different RDBMS vendors may have implemented their own variations and extensions, SQL has been standardized over decades. As a result, the consistency of SQL among different RDBMS is very, very high, and the variations are small. In the context of database design book, of course, SQL may seem less important. Database design doesn't necessarily require you to use SQL. Some database systems even come with graphical tools to generate SQL scripts that automatically create databases and tables based on your design. But having some understanding of SQL can make it easier to learn database design, especially when it relates to structural or design problems such as data integrity, optimization, and scalability. After all, SQL is a standardized language that most RDBMS uses, so knowing SQL will allow you to rely less on the graphical tools and work with different types of database systems. Next, you will learn SQL by executing your first SQL query. We will use the example that you saw in the preceding section, the database of the SciFi Collective. The database contains many tables. The database for the SciFi Collective, it contains many tables. But the product table is all you need to focus your attention on for now. The product table looks like this. The goal of our first query is simple. We aim at getting the product names whose price is above $20 from the product table. The query says select a name from product where price is bigger than 20 with a semicolon at the end. Before we break the query down and get to its details, let's run this query in an actual database first. You can find the GitHub repo that contains the data we showed to you in this video at this address. It's also linked in the description of this video. You can clone the GitHub repo to your local machine or download it by clicking the button of code here. Then there's a choice named download as a zip file. I already have the repo cloned locally on my machine, so I'm gonna open it in the VS Code environment. Everything you need is from the folder named Chapter 1. Here, in this folder, you can see a set of SQL scripts and a README file. Here. You can follow the instruction in the README file to install your preferred database system and run the prepared scripts accordingly on your local machine. However, here we will go with the easiest approach, which is to use a tool named SQL Online. Essentially, SQL Online is a database running on the cloud. Let's open that. As you can see, In the left sidebar, you can choose the target database system that you want to use. So you have 4 different options, including SQLite, MariaDB, Postgres, and MS SQL. So we are going to go with this choice, SQLite. That means we need to firstly import and run the prepared SQL script from the Chapter 1 folder. In our case, that file will be SQLiteOnline.sql. So we are going to import this file. If you ever get confused, you can use the README as a reference. It basically lists everything you need to do to get things done. Okay, so this is the target file, SQLiteOnline.sql. So let's import that file. We are going to click this import button. After that, we are going to click open and try our best to find the file. In my case, that file is saved in this folder named Grokking Relational Database Design, then Chapter 1, then SQLite Online. So I'm gonna click open. After that, I'm gonna click the OK button. There would be some info popped up telling you that the script has run. So what does the script do? The script handles creating a database and a table, then populate it with the same data that you saw from the last few slides. Before we write our first SQL query, let's take a look at the table again in this interface. So we are going to run this provided SQL query, select star, which means everything from the product table. And we are going to click run. As you can see, every row from the table has been presented here on the screen. Same as what you saw in the last slide. The 5 columns are product ID, name, description, price, and manufacturer. Product ID is the primary key. Note that all column names are lowercase. The same can be said for the table name. The 10 rows representing 10 different products. 5 of them are sold at a price below $20, and the other 5 are sold at a price above $20. After all these steps, you will be ready to query the product table. You can type the query into the code editor here on the SQLite Online interface. So that will be select name from product where price bigger than 20. After that, don't forget the semicolon. In the end, we are going to click run. As you can see, a single column of 5 rows, or say 5 product names, are returned. Congratulations on running your first SQL query. Just in case, if you have typos in the column name or table names, SQL will know and complain. For example, if we misspell the column name as names instead of name, if we click run, you are going to see some complaints from SQLite. So be careful with the column names. Well, how does the query achieve our goal? The part where price bigger than 20 may be a dead giveaway of what it does. The query retrieves the names of products whose prices are higher than 20. That's why it returns only 5 of them, I mean the 5 products that are sold at a price bigger than 20. Now let's break down the query and try to digest every bit of it. You may notice that this SQL query has a lot of similarities to plain English. To be specific, SQL is like English, but it comes with little to no small talk. And you don't have the same freedom in word choices when it comes to putting together a SQL query. You must use a set of SQL clauses and follow some rules. In your first query, you used the following 3 clauses. The first is the select clause. The select clause allows you to specify the columns you want to retrieve from a table. In your first query, you only asked for the name column, thus the select statement, or say the select clause, was select name. Second, the from clause specifies the source you want to retrieve the data from. It can be 1 or more tables. In your first query, you asked only for data from a single product table. Thus, the from clause was from product. Third, The where clause allows you to specify the conditions to filter the data retrieved by the select clause. In your first query, you want only the names of those products whose prices are higher than $20. Thus, the query was select a name from product where price bigger than 20. Last, you should always use a semicolon to indicate the end of a query. The semicolon essentially tells the database system that this is the end of a query, and anything that comes afterward will belong to a new query. Let's quickly review what we covered. You saw how messy a spreadsheet can get and why structure matters. You learned what a relational database is and how it organizes data into tables based on entities using primary keys. You also wrote your first very SQL query to retrieve data from a table. These are the essential building blocks of every modern database, and they're just the start. If you want to dive deeper into database design thinking, this series is based on the book Grokking Relational Database Design, which walks through these ideas step by step with real-world examples. The link is in the first comment. What was your biggest aha moment from this introduction? Or what still feels fuzzy? Please drop a comment. I would like to know where you're at. And if this helps to lay a solid foundation, feel free to like the video or subscribe to follow the full series. In the next video, we'll walk through the core building blocks of SQL, so that you can start reading and writing SQL queries with confidence.
Have you ever wondered how databases know exactly what data to show you and how to crunch the numbers too? In the next 15 minutes, you will learn how SQL filtering and aggregation work together to answer questions like which customers spent the most, or how many orders were placed last month. In this video, we will explore two fundamental concepts that are key to mastering SQL basics, filtering and aggregation. In case if you are new to SQL, we will start with a 2-minute refresher of the basic select from where query. Let's start with an introduction to the table that we are going to work with first. Think about an online store named the Sci-Fi Collective that sells only sci-fi products. Imagine that there's a table representing products in this database. There are 5 columns in this table, including product ID, name, description, price, and manufacturer. When the table is populated with data, it will look like this. We can ask a simple question that requires the help from a SQL query, like this. How do we get the names of the products that are sold at a price above $20? This query will help answer this question. Select a name from product where price bigger than 20. Then it's gonna be followed by a semicolon. You may notice that this SQL query has a lot of similarities with plain English. To be specific, SQL is like English, but with little to no small talks. But you don't have the same freedom in word choices when it comes to putting together a SQL query. You must use a set of SQL clauses, or known as statements. And you also need to follow some strict rules. In the query that you just saw on the last slide, you used the following 3 clauses. First, the select clause allows you to specify the columns you want to retrieve from a table. In this query, you only asked for the name column. As a result, the select clause was select name. Second, the from clause specifies the source that you want to retrieve data from. By source, I mean one or more tables. In this query, you only asked for the data from the product table. As a result, the from clause was from product. Third, the where clause allows you to specify the condition to filter the data retrieved by the select clause. In your first query, you only want the names of the products whose prices are higher than 20. As a result, the query that you put together was select name from product where price bigger than 20. Last, you should always use a semicolon to indicate an end of a query. The semicolon tells a database system that this is the end of a SQL query, and anything comes afterward will belong to a new query. That's a quick refresher of the SQL basics. Now let's dive deeper into the filtering topic. Filtering is a common data retrieval task. Whenever you need only a subset of data that meets some criteria, you will need the help of the where clause to filter the data. You just saw the application of the where clause in your first SQL query. However, it's worth to be more detailed in terms of what it means by a subset of data. To be more specific, a subset of data here means rows, a bunch of rows. The where clause filters rows based on the condition that follows. It doesn't care about the columns at all. Selecting which columns to include in the result is the job of the select clause. For example, if you want both the name and description columns in the result from the product table, you can list both of them one after another in the select clause and separate them using a comma, like this. In both of these two queries, the condition of the where clause is price bigger than 20. What if we have a different condition, such as products from a specific manufacturer, like Mad Inventors? To achieve this goal, we need to check if the manufacturer is Mad Inventors in the where condition. The query will look like this. As you can see, to check equality in SQL query, it's a single equal sign. You may also notice that the manufacturer name is wrapped up in single quotes. It indicates that this is a string data type. Does SQL have different data types? Yes. SQL data can be broadly divided into 6 categories, such as numeric data, string data, date or time, and more. In the product table, the data type of the price column is numeric. That's why you can filter price via the logical operators such as bigger than or equal to. The manufacturer column, on the other hand, contains only string data, and that's why you can compare manufacturer to Mad Inventors Inc., and also why this string Mad Inventors Inc. needs to be wrapped up in single quote, which indicates a string. We will cover data types in the future in detail. Now that you know how to filter both numeric and string data at least, you can create one filter that combines the two criteria by using some logical operators, such as AND or OR. For example, to get products that are made by the Mad Inventors Inc. and have a price below 30, you can construct this query like this. The query says select a star from product where price smaller than 30 and a manufacturer equal to Mad Inventors Inc. The AND operator combines the two conditions. Only the rows meet both conditions will be filtered and included in the result, which means that the products that are manufactured by Mad Inventors Inc. and have a price below 30. By the way, the order of the result rows don't matter at all. You shouldn't have any assumptions or expectations in terms of how the rows are ordered in the results. The star here indicates all columns, and that's why the result includes all columns from the product table. If you want to select all columns instead of specific ones, you can always use the help of the star symbol. We touched on 2 concepts that are relevant to filtering, including data types and logical operators. Now that you have seen enough on filtering, we are ready to move to the next topic, which is the aggregation. So what is aggregation about? Aggregation is about performing calculations on a set of rows to produce a single result. By aggregating data, you can gain insights into the trend and the patterns in the data that may not be visible at the individual record level. For example, you may want to count the number of rows in the product table, and that will tell you how many products are sold by the online store The Sci-Fi Collective. To achieve that, you can write your query like this. Select count star from product. If there are 10 rows in total, or say 10 products in total from the product table, the result will look like this. You may notice that the count follows by a bracket, which is used to wrap up the star. In other programming languages, this is a sign for functions. The same can be said for SQL queries. Count is a function that counts the number of rows, and it takes a single parameter. Regardless of if you gave it a star representing all columns or a single column like name, it leads to the same result because it counts the number of rows in the product table. Aggregation is about performing calculation on a set of rows to produce a single result, and the calculation relies on using some of the existing functions in SQL. Some of the most frequently used aggregation functions include count, sum, average, max, and min. As you can see, the names tell a lot about what they do. For example, AVG function calculates the average value in a numeric column. For another example, max finds the max value in a column. All functions are structured the same. The function name is followed by a round bracket. Most functions are only applicable to a single column with proper data type, except for the count function. Let's see a few examples of the aggregate functions to get a better sense of how they get applied. Think about we are still dealing with the product table from the Sci-Fi Collective database. Our goal this time is to calculate the average price of products that are made by Mad Inventors Inc. If you find this overwhelming, you can take a step back to get all the prices of the products that are made by Mad Inventors Inc., which will be translated to a query like this. Select price from product where manufacturer is equal to Mad Inventors Inc. The Mad Inventors Inc. is wrapped up in a single quotes because it represents a string. Having access to all the prices of such target products makes calculating the average price simple. All you need to do is to apply the corresponding aggregate function average to the price column in the select clause, like this. The result of this query will be a data point in a single row and a single column, representing the average price. Its column name by default could simply be count bracket in many database systems. If you don't want to settle with the default column name, you can use the as clause to rename it, like this. And the result looks like this. As you can see, the name up to your choice that follows the as clause will be used to name this column. Let's look at another example to learn how to perform aggregation by groups. This time, our goal is to get the number of products per manufacturer. This goal requires us to group products by manufacturer first before counting the number of products per group. To achieve this goal, we need the help from a clause we haven't seen yet. The query that achieves this goal and the result are presented here on the screen. The result is literally product numbers grouped by manufacturer. This query is using a clause that we didn't cover in the past, which is the group by clause. The group by clause in SQL is used to group rows that have the same values in one or more columns so that you can apply aggregate functions to each group individually. In this example, we grouped the rows in the product table by manufacturer. After that, we applied the count function to count the number of rows in each group. That's why this query helps us achieve the given goal. Now you know what group by does, and how it is used in concert with aggregate functions. Let's talk about what you need to pay attention to when it comes to aggregation by groups. First, the group by clause is rarely used alone. It is used with one of the aggregate functions. In such a case, you need to remember to include the column followed by the group by clause in your select clause. For example, in this query, as you see here on the screen, we group rows from the product table by manufacturer. So we need to make sure that the manufacturer column shows up here in the select clause. Why? If you forget to do so, your result will become something that's very difficult to interpret. For example, you may forget to include the manufacturer in the same query that we just covered, and you will get a result looking like this. What does the query do? The query still does the same thing. Group rows by manufacturer and then count the number of rows per group. However, when you forget to include the manufacturer as a column in the select clause, the manufacturer information won't show up in the result. So the product numbers per group is kind of pointless standing by itself. Okay? That's one of the important things about the group by clause. Another important thing about the group by clause is that you need to remember to exclude any irrelevant columns in the select clause when you are doing aggregation by group. Specifically, you need to exclude any columns that are neither in the group by clause or the aggregate function. Otherwise, SQL will complain. For example, when you try to add another irrelevant column to this query, like the name column, you will get an error message like this. When using group by clause, you need to make sure two things. First, you need to include the grouped column in your select statement. Otherwise, you may end up with a confusing result. Second, you need to avoid selecting columns that are not in the group by clause or inside an aggregation function. Otherwise, SQL will throw an error. In case if you wanted to run the queries that were covered in this video and replicate what you saw, you can find everything you need from this GitHub repository. The URL of this repository can be found in the description of this video. The easiest way to replicate what you saw from this video is to load data into a tool named SQL Online. You can follow the README files in each of the corresponding folders, for example, Chapter 1, to see the detailed instruction. Of course, you can follow the instruction to install your preferred database system locally and then load the scripts, but we are going to simply use a tool that makes things easier for us to start. The tool is named SQL Online. Essentially, that's a SQLite database system running on the cloud. Once you follow the instruction in the README file to load the corresponding script from what we prepared for you, you will be able to run all the queries that were covered in this video and see the same results. Let's quickly recap what we covered. We started with a very basic SQL query, and then explored two fundamental concepts based on that, filtering and aggregation. If you find this video helpful, give it a thumb up, subscribe, or drop your questions in the comments. I would love to hear what's working for you and what needs to be changed. If you wanted to go deeper into database design, this video is based on the book Grokking Relational Database Design, which walks through these ideas step by step with real-world examples. You'll find the link to the book in the first comment. Are you just starting SQL or need a quick refresher on the SQL syntax? In this video, we will walk through how to create tables, modify them, and manage data. All with clean, non-fluffy examples. No theory, just the exact SQL that you need to get things done. In this video, we will learn the basics of table and data management using SQL. Specifically, you will learn the commands related to table management and data management. Let's get started with table management first. And the first thing you need to know is how to create tables. Creating a table using SQL requires the help from the create table command. To demonstrate how it is used, let's think about creating the product table for the database supporting the online store named the Sci-Fi Collective. So as you can see here on the screen, the product entity has 4 different features, including name, description, price, and manufacturer. To create such a table, plus adding a primary key beyond these 4 different features, the command will look like this. To understand how this create table command works, we need to answer 2 questions at least. First, what is the general syntax for creating a table using SQL? Second, what do the different keywords do in this query example? What's the general syntax for creating a table? The general syntax looks like this. The command starts with create table keyword. Then it's going to be followed by the table name of your choice. In the round bracket, you need to define all the columns of the table. Each line will start with the column name, then followed by its corresponding data type. Lines are separated by commas. You also need to define the primary key of the table. You can define that using a separate line like this. The keyword primary key is going to be followed by the column name inside a round bracket. Or you can put the primary key keyword after a column which you want to use as a primary key. That's the general syntax. The example that we showed you a few moments ago followed the syntax strictly. Product is the table name. Primary key is followed by the column name product ID. These two things are required to create a table in general. In addition to that, you may also notice the different data types for each column. Product ID is a numeric column, integer actually. Name, description, and manufacturer are all string columns. Price is also numeric. It's a decimal column. Here we use decimal 52 to define that the price column will allow 5 digits in total and 2 digits to the right of the decimal point. In the future, when it comes to discussing the choice of appropriate data types for columns, we will go over the differences between integers and decimals. Last, you may also notice that all the columns except for product ID are declared not null. That means those columns don't accept null values. In SQL, a null value represents an unknown value, similar to when you are trying to remember someone's name and it's on the tip of your tongue, but the value either is missing or unknown. Allowing null values for columns may lead to SQL to have unexpected behaviors. For example, when you try to add 10 and a null value, you will end up with a null value. The sum of an unknown value and a 10 is still unknown. When you do calculations on null values, all the results may all end up as null. Then you may wonder whether the product ID column as the primary key column would allow null values, and why we didn't declare it as not null. The reason for that is this column, product ID, has already been declared as the primary key. Thus, we'll make sure that the product ID column will not allow any null values. So there's no need to further declare this column as not null. Now you understand how to create tables. From time to time, you may need to alter the structure of a table, or even drop a table, because, let's face it, sometimes you need to rearrange furniture in your data house. There are many ways to alter a table, such as adding a column, modifying the data type of a column, or renaming the entire table. You can rely on the help of the alter table command to perform all these tasks. The general syntax of altering a table is simple. It's simply the keyword alter table. Then it's going to be followed by the table name. After that, you need to specify what changes you want. For example, if you want to add an integer column to the product table representing serial number, you can do this. Alter table product add a serial number, then integer. This command, when being executed, will lead to changes like this. For another example, if you wanted to change the data type of the column serial number from integer to text, you will write it as alter table product alter column serial number text. However, it's worth noting that different database systems may vary in terms of what's allowed and what's not on altering tables. For example, SQLite doesn't allow changing column data types. You have to delete the old column and add a new one to achieve what you want. you will need to check the manual of your target database system on this. Although you have many ways to alter a table, there is only one way to drop a table. You will use the help from the drop table command. The general syntax is simply drop table keyword, then followed by the table name. For example, if you want to drop the product table, the command will simply be drop table product. However, you need to be careful when using the drop table command because it will permanently delete the table and all its data. Now you learned everything you need to know about table management. Let's move to data management. We will start with how to add data to a table. When the product table is created in the database, it's ready for you to add data to it. To add data to a table, you need the help from the insert into command. The insert into command allows you to insert one or more rows of data into a table. Here's the basic syntax of adding data into a table. You will start with the insert into command. After that, it's gonna be followed by the table name. Then, in the immediate round bracket, you can list all the column names. Then value keyword is gonna be followed by the values of different rows. Each row is encapsulated in a round bracket, and the rows are separated using commas. The order of the values in each row need to correspond to the order of the column names that you specify here in the first bracket. For example, you can insert a single row into the product table like this. Notice that the order of the values correspond to the column names. If you change the column name order, you also need to change the order of the values. For example, we can change the order of the product ID and the description, like this. Then, the order of the values also need to be updated, like this. If you have more than one rows to add to a table, you will simply list them one after another and separate them using commas, like what you see here on the screen. This command adds 2 rows into the product table. Now you know how to add data, specifically rows of data, into tables. Let's move to discuss how to delete data in a table. The general syntax of deleting data in a table is as follows. Delete from command is gonna be followed by the table name. After that, you need to specify a filtering condition. Essentially, this command will delete the rows that meet the given filtering condition from the table that you specified. An example of the delete command is as follows. Delete from product where product ID is equal to 2. This command will delete the row whose product ID is 2 from the product table. When deleting data from a table, you need to make sure to specify your filtering condition. Otherwise, the consequence can be serious. Without a filtering condition, the command delete from product will delete all the rows from the product table. In other words, all the data will be gone, even if the structure of the table is intact. That's everything about the delete command. Let's move to discuss how to update data in a table. This task requires the help from the update set command. The syntax of such a command is as follows. It will start with the update keyword, then it's gonna be followed by the table name, then set. The set keyword is followed by the details of how you want data to be updated in the corresponding column. In the end, you need to specify a filtering condition. After all, this command aims at updating data of specific rows. An example of an update command is as follows. Update product, set price as 18, and name as not a toaster when product ID is equal to 2. This command will update both the price column and the name column in the rows whose product ID value is equal to 2. Same as the delete command, the filtering condition is very important here. Without a filtering condition, An update command will update the specified column in every row. For example, the command that you see here on the screen will update the price to 18 and the name to not a toaster in every row in the product table. That's highly unlikely to be a case that you want. So the filtering condition is critical when it comes to deleting or updating data in a table. In this video, you'll learn the basics of table and data management, such as how to create, alter, or drop a table, insert, update, or delete data in a table when needed. This wasn't meant to be an exhaustive list of SQL commands, but it's an important step towards mastering database and a solid database design. If you find this video helpful, give it a thumb up, subscribe, and drop your questions in the comments. I would love to hear what's working for you and what needs to change. If you want to go deeper into database design, this video is based on the book Grokking Relational Database Design, which walks through these ideas step by step with real-world examples. You'll find the link to the book in the first comment. A database is more than just a collection of tables. It's a web of relationships. If you have ever struggled with broken data, confusing joins, or unexpected deletes, the root cause might be right there. Let's define what related tables are and how foreign keys hold the web of tables together. In this video, you'll learn the basics of related tables and how such tables and their data are managed. Let's get started by defining related tables first. So what makes two or more tables related to each other? Let's use an example to explain this concept. Think about an online store named the Sci-Fi Collective that sells sci-fi products online. There are two tables in its database. One represents the products that are sold, while the other represents the reviews associated with the products. Since each review is for a specific product, the review table needs the help from the product ID column to remember which review is for which product. As a result, the two tables share a common column, the product ID. If you need to see what the two tables look like with some data in them, here you go. As you can see, the value in the product ID column helps connect a row in the product table and a row in the review table. For example, in the product table, there's a row with a product ID value as 3. It records a product named Cat Poop Coffee. In the review table, the row with a review ID value of 1 records a positive review for this product. How would you know the review is for the Cat Poop Coffee? The two rows here have the same product ID value. That's why. So the product ID column is shared across the two tables. Its goal is to help the review table remember which review is for which product, and that makes the two tables related to each other. In the product table, the product ID column is the primary key. In the review table, the product ID column is known as the foreign key, which refers to the primary key of another table. In this case, the other table is the product table. Now let's define the related tables formally. The related tables are the tables that are connected by one or more common columns in a database. As curious as you are, you may wonder whether product and review tables can share a few more columns beyond the product ID. That's a great question about database design. You can even generalize this question a bit to all related tables, like this. Should the two related tables share columns beyond the primary/foreign key? The answer is no. To simplify our discussion, let's look at the scenario in which two related tables use single columns as the primary keys, the product and the review table. Theoretically speaking, the numbers of columns shared by the two related tables can range from only the primary/foreign key to all columns from both tables. Using the product and review tables as an example, the figure that you see here on the screen summarizes the spectrum, so it ranges from just one column on the very left side to all the columns on the very right side. If two related tables share every column, I mean the same as what you can see here on the right side of the spectrum, it's obvious that one of them is redundant, and that's unnecessary. If you choose to delete one of those two tables, you will still find trouble in the remaining one. I mean, this is a scenario where you use one table to represent two entities, and that will lead to insertion or delete anomalies and tons of redundancies. Even with just a few rows, as you can see here on the screen, you can still spot the redundancies. Okay, making two tables share every column is apparently a bad idea. How about making the two tables share only a few columns, such as one or two more columns beyond the primary/foreign key? That's also a bad idea. First, you would still have redundancies, even if it's less serious than a redundant table. Second, you will set a trap for yourself when you need to update data in such tables. If you update data in only one of the two related tables, but forget the other, you will end up with inconsistent data. Suppose that you decide to make the product and the review tables share one more column beyond the product ID column, the manufacturer column. When you need to update the manufacturer of a product, you need to update both of the product and the review tables. Otherwise, you will end up with new manufacturer data in one table, but outdated data in the other. Such a problem is known as an update anomaly. That said, given two related tables, they should share the primary/foreign key. If the primary/foreign key is a single column, then the two tables should share that column. If the primary/foreign key is composed of one more columns, then the two tables should share those columns. However, they shouldn't share any other columns beyond the primary/foreign key. Now you know what the related tables are. Let's move to discuss how to manage related tables. We will start with the foreign key constraint. So to properly introduce the foreign key constraint, we will use an example and start with a question. How do you create two related tables? For example, how do you create the product and the review tables for the database of the Sci-Fi Collective? Well, you can actually create the product table in the same way as if you are going to create a single table that's independent, that's not related to any other tables. Okay? You can rely on the help of the create table command, then that's gonna be followed by the table name, then a bracket. In the bracket, it will wrap up all the columns line by line, separated by commas. In each line, it will list the column name and the data types. You are also required to specify which column will be used as the primary key. But what about the review table? The review table can be created with the help of this command, as you can see here on the screen. This is still a create table command, of course. However, there might be some clauses that you see for the first time. To explain this clearly, we need to discuss the general syntax of creating related tables first. So what's the general syntax for creating two related tables, or say two tables that have a relationship? As you know, the shared column product ID is the primary key in the product table, and the foreign key in the review table. Given a pair of two related tables, we call a table like the product the parent table because it uses the shared column as the primary key. We call the table like the review the child table because it holds the foreign key. As you can see from the command that creates the product table, the syntax for creating a parent table is the same as the syntax for creating a single table that's not related to any other tables. To create a child table, you need to specify the foreign key that references the primary key in the parent table. You still need to define all the columns, data types, and the primary key, of course. The general syntax for creating a child table is presented here on the screen. Alternatively, you can create the two tables independently and add the foreign key constraint to the child table afterward, like what you see here. In both options, you saw the constraint foreign key clause. What does it do exactly? In short, the clause creates a foreign key constraint, which serves as a link between the two related tables. The constraint is twofold. On one hand, the constraint ensures that the foreign key column in the child table references only valid primary key values in the parent table. On the other hand, the constraint ensures that updating or deleting of rows in the parent table doesn't violate the consistency between the two related tables. We refer to these two aspects as referential integrity. So this long clause with three keywords, constraint, foreign key, then references, enforces referential integrity between two related tables. Referential integrity is an important aspect of data integrity. This clause is composed of two parts. The foreign key references statement creates a foreign key constraint that enforces the referential integrity. What about the constraint part? The constraint clause allows you to name this constraint. When you create a foreign key constraint, you don't necessarily need to name it, but naming it will make it easier to access whenever you need to modify such a constraint in the future. For example, in this example that you see here on the screen, we name the foreign key constraint in the review table as fk, short for foreign key, then product, then review, concatenated by underscore. As you can see, foreign key, then product table, then review table. That's how the name is made. If you ever need to drop this constraint, you can access the constraint via this name, like what you see here on the screen. If you don't name a constraint yourself, the database system that you use will name it automatically for you. The database system will use a default naming convention. Although the automatically picked name can be retrieved, the name and the default naming convention vary from one system to the other. To avoid this hassle, we would recommend you always name the constraints. After all, dropping or disabling a constraint can be a common task whenever you need to modify your database design. Now you know how to create related tables and declare foreign key constraint. A natural question to ask next is whether the foreign key constraint have an impact on adding data into tables. Well, the short answer is yes. We mentioned this briefly when we talked about the referential integrity, but here we want to show it to you very explicitly using examples. First, adding data into the parent table is not impacted. It's the same as if you were to add data to a table that stands alone. For example, this command adds another row to the product table. As the product table is a parent table, there's no impact from the foreign key constraint at all. Second, adding data into child tables is impacted by the foreign key constraint. It's manifested in that every row added into the child table needs to have a product ID value that corresponds to an existing product ID value in the parent table. For example, if you ever try to add a row into the review table, but this row's product ID value doesn't correspond to anything in the product table, like this, where 3000 doesn't exist as a product ID in the product table. You will receive complaints from SQL. If you think about it, such rows of data shouldn't exist in the database in the first place. If you are ever allowed to add such data into the review table, it only introduces troubles in the future, such as inconsistency and the trouble to figure out what non-existing products are referred to. That's how foreign key constraints protect the data integrity in your database. Deleting data from parent tables is also impacted. For example, if you try to delete the third row from the product table, the row whose product ID value is 3, then you are going to rely on the help from this query. Delete from product where product ID is equal to 3. When you try to execute this query, you will get complaints from SQL because this product has been linked to multiple reviews, in the review table. If you are allowed to take this action, you will end up with some orphan rows in the review table that references some product ID values that can never be found in the product table, which will introduce a lot of troubles in the future. That's how foreign key constraints protect the data integrity of your database. For almost the same reason, you can't update the primary key value that's referenced in a child table. When you try, you will get errors from SQL. Beyond data management, foreign key constraint also has an impact when it comes to dropping related tables or updating table structure. Given two related tables, like product and review, in the database for the online store Sci-Fi Collective, if you try to drop the parent table or change the parent table structure, such as renaming the primary key column or changing the primary key column from product ID to something else, you will certainly get complaints from SQL. If such changes can get through easily without any constraints, they may lead to many issues in the future and harm the data integrity of your database. If you really want to perform such tasks, you will need to drop the foreign key constraint first, and in the eyes of the database system, that is an explicit agreement that you understand the consequence of doing such a thing. So then you will be allowed to perform such tasks. In this video, you'll learn about related tables and how to manage related tables and their data. You also picked up some new concepts such as foreign key constraints and data integrity. If you are finding this video helpful, give it a thumb up, subscribe, and drop your questions in the comments. I would love to hear what's working for you and what needs to change. If you want to go deeper into database design, this video is based on the book Grokking Relational Database Design, which walks through these ideas step by step with real-world examples. You'll find the link to the book in the first comment. If you are ever being confused by SQL joins, especially how joins actually work, and the difference between different types of joins, you are not alone. In the next 15 minutes, we'll explain everything related to joins and break it all down with clear examples. In this video, you'll learn how to join data from related tables and dive deep into different types of joins and the comparison between where and join clauses. Let's get started with how to join data from related tables first. From time to time, you may get a task that requires you to query data from related tables. For example, think about the online store named the Sci-Fi Collective. There are two tables in its database. One represents the products that are being sold, while the other represents the reviews of products. Since each review is for a specific product, the review table needs the help from product ID to remember which review is for which product. As a result, the two tables share a common column, the product ID. The product table is the parent table, while the review table is the child table in this relationship. If you need to see what the two tables look like with some data, here you go. If you ever want to understand how products are reviewed, you will need to pull data from both tables, at least the name column from the product table and the review text column from the review table. Of course, as you do that, you need to map each review to its corresponding product. The query that answers your question looks like this. Select the name, review text, from product, join review, and product.productID equals review.productID. This query takes advantage of the join on clause to join data from two tables. As you may have guessed, the join on clause here in this query maps each review to its corresponding product and makes sure that the result contains only the properly mapped products and their reviews, as you can see here in the result sample. Although this query looks straightforward, we do need to explain a few things, answer a few questions, so that you can have a thorough understanding of how join actually works. First, what's the general syntax for retrieving data from related tables? Second, what does the join on clause do? And third, what's the dot notation and how do we use it as in product.productID and review.productID? So the general syntax first. The general syntax of joining data from related tables is presented here on the screen. We have some assumptions here, which is that the two tables, I mean table 1 and table 2, are actually related. The two tables are listed here. From table 1, join table 2. The condition of the join is listed here on table 1 dot column equals to table 2 dot column. This is a shared column between the two tables. In the select clause, it will list the target columns that you want to show up in the result. So that's the general syntax. Next, what does the join on clause do exactly? The answer to this question has two parts. First, the join clause computes the Cartesian product of the two tables. Second, the on clause filters the result based on the given condition. What's the Cartesian product? The Cartesian product between two tables is the set of all possible combination of rows from the two tables. Think about the product and the review tables. To produce their Cartesian product, it will grab every row from the product table, and then combine it with every row in the review table. For example, if the product and the review tables each have only 3 rows, we will start from the first row in the product table, and combine it with every row in the review table, and the combined rows all go into the results. The same can be said for the second row in the product table. It will be combined with every row in the review table, and they all go into the result. The third row in the product table is no exception. It will be combined with every row in the review table, and they all go into the result. So in the end, the join clause by itself produces a Cartesian product of 9 rows. Even if many of the combinations don't make much sense, we don't care here. All we care is to produce a result of all possible combinations of rows from the two tables. That's why the example Cartesian product has 9 rows. That's 3 multiplied by 3. Remember, the product table has 3 rows, and the review table has 3 rows. When you multiply 3 by 3, you get 9. Okay, that's the first part of the answer. So what does the on clause do next? The on clause applies the filtering condition to the Cartesian product, and only picks the rows in which product.productID is equal to review.productID. In short, the on clause picks the rows where mapping between a review and a product makes sense. In the end, the select clause only picks the 2 target columns, names and review text, and returns them as a result. So on the screen, only the cells within the red highlighted rows and columns would be included in the result. Now you know what the join on clause does. Let's move to the next question. So what's a dot, and how do we use the dot notation as you see in the product.productID and review.productID? Well, the dot notation is a SQL syntax that's used to separate parts of a name. Product.productID, for example, refers to the product ID column in the product table. For another example, product.name can refer to the name column in the product table. Dot notation is especially handy when you query related tables because it helps you to be specific about the columns in case they have same name, such as product.productID and review.productID. This approach makes it clear which column and which table you are actually referring to so that it can prevent confusions. Beyond that, if 2 tables that you want to join have multiple columns that share a name, you may want to rename them in the select clause to prevent confusions. For example, you have 2 related tables, employee and department here on the screen, and you want to join them to get the names of the departments to which employees belong. However, both tables have a column named name, so you need to use the dot notation to specify which name column to select. So the query that gets the job done properly will look like this. Select employee.name, department.name. From employee, join department on employee.departmentID equal to department.id. The ID in the department table is the primary key, and its corresponding foreign key in the employee table is named department ID. It's worth mentioning that the result may show two column names that look exactly the same, like this. To prevent this confusion, you can rename the columns with an alias via the as clause, like this. All it takes is to add an as clause that follows the actual column names, so that you can specify how the column names should show up in the result. Okay, that's everything about how to join data from related tables. Let's move to discuss the different types of joins. So this is the general syntax of how to use the join on clause to join data from two related tables. There are actually more than one type of joins, and the join keyword can be replaced by the following options, including inner join, left join, right join, and a full outer join. Different types of joins will give you different results. The inner join is the same as join and returns only the rows that have matching values in both tables. In contrast, left join returns all the rows from table 1 and the matching rows from table 2. If a row in table 1 has no match in table 2, the result row will include the table 1 record with null values for table 2 columns. For example, the left join between the product and the review table will lead to a result looking like this. Every match between the product and the review tables will be included. Beyond that, the products that have never been reviewed will also be included. For example, the atomic nose hair trimmer was never reviewed. It will still be included in the result, but its review text value will be null because it doesn't have a match from the review table and there is nothing to fill up that cell. Right join returns all the rows from the table 2 and the matching rows from table 1. If a row in table 2 has no match in table 1, the result row will include the table 2 record with null values for table 1 columns. Full outer join returns all the rows from both tables, including the non-matching rows. If a row in table 1 has a matching row in table 2, the corresponding result row will simply include the data from both tables. If a row in table 1 has no match in table 2, the result row will include the table 1 record with null values for table 2 column. Similarly, if a record in table 2 has no match in table 1, the result row will simply be the table 2 record with null values for table 1 column. The relationships among the left table, the right table, and the returned results are summarized here on the screen. It's worth noting that the left join, right join, and full outer join may lead to query results with null values. One side effect of getting null values in the result is that you need to handle them very carefully. Null values can cause errors if you try to perform calculations or comparisons. Okay, that's everything about the different types of joins. Let's move to talk about the comparison between where and the join clause. As curious as you are, you may be tempted to try to join in two tables using the where clause. Can you do that? Yes, you can. You can certainly use the where clause to join two tables as long as they are related. The two examples that use join clause and the where clause to join tables are listed side by side on the screen. To use the where clause to join data from related tables, you need to list the two tables one after the other in the from clause and separate them using commas. And the where condition is used to do the filtering. Both of the two queries work and achieve what you want. However, whenever you need to query related tables, the join clause is generally preferred. There is a strong evidence that people make less mistakes using explicit join than the where clause, so it's less prone to errors and more straightforward to modify or debug. Beyond that, the join clause is typically much more optimized by database system engines than the where clause. So using join clause does give your database a better performance than using a bunch of where clause to join tables. In case if you wanted to run the queries that were covered in this video and replicate what you saw, you can find everything you need from this GitHub repository. The URL of this repository can be found in the description of this video. The easiest way to replicate what you saw from this video is to load data into a tool named SQL Online. You can follow the README files in each of the corresponding folders, for example, Chapter 1, to see the detailed instruction. Of course, you can follow the instruction to install your preferred database system locally and then load the scripts, but we are going to simply use a tool that makes things easier for us to start. The tool is named SQL Online. Essentially, that's a SQLite database system running on the cloud. Once you follow the instruction in the README file to load the corresponding script from what we prepared for you, you will be able to run all the queries that were covered in this video and see the same results. In this video, you took a deep dive into the join clause, learned about how join actually works, the different types of joins, and the comparison between the where and the join clause. If you find this video helpful, give it a thumb up, subscribe, and drop your questions in the comments. I would love to hear what's working for you and what needs to change. If you want to go deeper into database design, this video is based on the book Grokking Relational Database Design, which walks through these ideas step by step with real-world examples. You'll find the link to the book in the first comment. Many people still try to learn SQL the old way, watching endless tutorials, or trying to memorize syntax like it's 2010. But in 2025, that strategy will cost you time, money, and momentum. Today, tools like ChatGPT can write most SQL queries for you. So your job isn't to memorize syntax. Your job is to know what to ask, why it works, and how to structure your data to get the results you need, or gain insights that shape your database design. In the next 10 minutes, I'll show you a smarter and faster way to learn SQL, one that leverages AI while helping you truly understand what's happening under the hood. First, what not to do. A lot of people begin their SQL journey with this pattern. Learn select, then where, then join, then just keep practicing until it sticks. You'll watch tutorial after tutorial that walks through query after query, showing the same surface level pattern, but never really explaining what's going on underneath. They might teach you how to join two tables, but not how the join works and what an Cartesian product is. They'll show you the syntax for where, but skips over how the database engine actually processes that filter. This is like learning to recite a song in a foreign language without knowing the meanings of any words. Here's the problem with this approach. You don't build real understanding, and you may get stuck the moment your task becomes even a little bit complex. And this approach of learning will set you up for directly competing with AI, and you know that you will lose even now, let alone in a few years. So what to do instead? We wanted to highlight at least two things that you should consider doing. First, you wanted to go beyond simple SQL syntax to learn how to design smart questions that can be translated to SQL queries by generative AI. Different from most programming languages like Java or Python, SQL is declarative. By saying that, I mean SQL is more aligned with natural languages. When you deal with SQL, you only need to describe what results you want, not how to compute it step by step. This makes it exceptionally well suited for AI tools like ChatGPT or Copilot for various reasons, such as that SQL has a limited and consistent structure,
And there's no control flow or state tracking in SQL. AI can generate correct or even optimized queries with just a plain English prompt now. So in most cases, you don't need to write the syntax by hand. You can delegate that part. The more important skill is shifting your role. The new challenge isn't how do I write this query. It is instead what exactly am I trying to find out from the data. That sounds simple, but it's actually a higher order thinking skill. AI can't offer much help if you don't know what you are looking for. Learning SQL today means learning how to translate your real-world questions into something a database can understand. To do that well, you need to know the language of data. You need to understand what a table is, how relationships between entities work, how joins work, and how your data is structured. Sometimes you even need some domain knowledge, like what active users mean in a marketing context, or what a transaction is in a financial dataset. So yes, you are offloading the mechanics, but you are upgrading the strategy. And here's the best part. Once you get good at designing smart questions in SQL, you'll get better at asking the right business questions, designing dashboard, exploring data, or even writing better prompts for other AI tools. You are not just learning SQL. You are learning to think clearly about data, and that's a competitive edge across different fields. Second, you should focus on why and how behind and beyond SQL queries. One of the most underrated ways to learn SQL, especially today, is to learn it in context. Think of learning SQL like learning a new language. Sure, you could memorize vocabulary lists and grammar rules, but you will learn faster and retain more if you're actually using it in an authentic activity, like reading or conversation. The same applies to SQL. Instead of keeping practicing isolated queries, you need to connect the SQL to real tasks that matter to you. That's how you start uncovering the why and how behind each line of SQL that you write. If you are aiming to become a software engineer, a great entry point is to learn database design. Why? Because when you learn database design, you are forced to think about what data types to use, how tables relate to each other, and how to structure the data for future queries and applications. Take a simple example. Suppose you decide between using datetime and a timestamp for a column. At the first glance, they may seem interchangeable, but datetime just stores the date and time as it is, whereas timestamp is stored in Coordinated Universal Time, short for UTC. A time stored in this format can be automatically adjusted for time zones when the data is read. If you're building a global app, this seemingly small choice can lead to big problems or save you from one. These kind of details, the ones that you don't see in most tutorials, are exactly what you better at SQL in the long run. If you're on the data analytics path, your best teacher is real data. An actual realistic and possibly messy dataset from an actual relational database. Try using the data to build a dashboard, generating reports, or answering real business questions. Here's what I mean. Instead of learning group by in isolation, try calculating weekly retention from actual event data. Instead of just filtering rows, try preparing selected product data for a sales dashboard. Instead of writing a drawing just because your course told you so, try explaining user conversion rates across different sign-up flows. This way, you are not just asking how do I write this query. You are asking what does the metric mean? What shape does my data need to be in? Or how can I make this accurate and useful? The bottom line is this. You will learn SQL more deeply if you stop treating it like the end goal. Use it to design and implement databases. Use it to answer better questions. That's how you will get good, and that's how you will stay ahead, especially now AI can write nearly all the queries for you. Now you know what not to do and what to do to speed up your mastery of SQL. Let me introduce a learning roadmap that encapsulates these ideas. A smart learning roadmap still starts with mastery of the fundamentals. By saying that, I mean you still need to learn how to write SQL like select, from, and where clauses,
But don't stop there, and don't drown yourself with similar SQL practices. Instead, what really separates effective learners from those who get stuck is this. The effective learners understand the relational model that SQL is built on. For example, understanding what a table really is, not just a spreadsheet of data, but a set of tuples that follows a schema, changes how you think about joins, keys, and constraints. For another example, the understanding of foreign keys shouldn't just be limited to their technical details. Foreign keys define relationships between entities and shape how you design your queries and your database. A lot of people know the syntax of join clauses, but they can't tell you how the difference in cardinalities impact how you write the join queries. Another key idea is set-based thinking. SQL operates on sets, not rows. That's why functions like count, group by, and distinct behave the way they do, and why you can't always think procedurally. These concepts may sound academic, but they are exactly what gives you the confidence when reading, modifying, or validating AI-generated queries. So yes, learn your syntax, but if you want to learn SQL faster and retain it longer, focus on the core ideas behind it. Understanding the relational model is more important than memorizing syntax, and that foundation will pay off again and again as your projects grow more complex. If you want to get really good at SQL, you need to go beyond just writing queries, and what that means depends on what you are learning SQL for. If you are on the path of software engineering, learn SQL in isolation is like learning vocabulary without knowing how sentences are structured. You need to understand how databases are designed, because design decisions directly impact how queries work. For example, after learning various aspects of database security, you will know that password encryption only demands increasing the varchar size of the password column, but not necessarily the data type, because one-way hashed passwords require a bigger data storage, but can comfortably stay as characters. Such a change is critical, yet may seem so trivial and ridiculous in the eyes of those who limit their learning to just SQL itself. So if you're aiming to become a software engineer, go deeper into database design. This is where theories matter, not in a purely academic way, but in a way that changes how you build software systems. If you are serious about this path, I have some resources to recommend. The Book of Database System Concepts, a time-tested academic classic, which is in its 7th edition now. If you want an easier entry into this topic, grokking relational database design could be a choice. It's a modern example-driven approach that works for self-learners and developers. As a disclaimer, I'm the lead author of this book. However, if you're learning SQL for data analytics, your learning journey should focus on how SQL fits into the larger data analytics pipeline. SQL is the tool that you use to ask questions from real data, but what makes those questions meaningful is the context of your analysis task. For example, instead of learning group by in the abstract, it will be more productive if you try to analyze user behavior from a website log, or track sales performance over time, or segment customers by purchase pattern. These aren't just exercise. They teach you why you need certain joins or filters, and how to structure queries for insights, not just for correctness. Taking on projects like building a dashboard or generating a weekly report for stakeholders gives you a reason to apply window function, nested queries, all in a real-world context. In addition to that, you will be naturally exposed to related tools like Excel, Power BI, or Looker Studio, or even Python libraries like Pandas or SQL Alchemy, or data cleaning and transformation steps that complement SQL. A great way to accelerate this kind of learning is to pick up datasets that you care about, public dataset, sport dataset, financial dataset, or anything, and challenge yourself to tell a story with it using SQL. So whether you're building an analysis pipeline or telling a data-driven story, going beyond queries means understanding how SQL fits into the bigger picture of the problem you are solving. Once you have built the foundations and gone beyond just the queries, the best way to level up is by working on real projects. Projects that give you a context, purpose, and clear goals. They connect everything you have learned.
If you are learning for software engineering, start building databases from scratch. Such activities will force you to think about data integrity, normalization, and how your schema decisions affect how SQL behaves. As I record this video, I realize that authentic problems on database designs are scattered and their qualities are uneven. So, I'm currently working on a public GitHub repo to aggregate quality problem sets on database design and implementation. The URL of this repo is here. You can find the link to this repo in the description of this video as well. Remember that you don't need a perfect idea or a big plan. The key is to start doing something small, messy, and real. That's where the real learning happens. That's how you go from a student to an expert. If you are learning for data analytics, then your focus should be on querying, analyzing, and communicating insights. Pick a public dataset from Kaggle, Google Dataset Search, or data.gov. Import it into a database system. Start with simple questions like what are the top 5 cities by population growth, which product category has the highest return rate, or how has revenue changed month over month. Then go deeper, group by, filter, join with another table, and try visualizing your results. Try to answer a real question as if you were building a report for a stakeholder. And again, write up your analysis, push your queries and charts to GitHub, share your data analysis on Kaggle. This gives your learning a purpose, and it builds a public track record of your growth. In this video, we explored how to learn SQL deeper and better. Such a discussion becomes unavoidable when generative AI tools can write accurate and even optimized SQL queries given a proper prompt. If you find this video helpful, give it a thumb up, subscribe, and drop your questions in the comments. I would love to hear from what's working for you and what needs to change. Ever get charged twice for the same thing? Or see your Uber driver's name change mid-ride? It's not a bug, it's a bad database design. Behind every confusing, slow, or broken app, there's probably a database screaming for help. In this video, I'll show you the 5 goals every great database must achieve, and why ignoring even one of them can cost your user money or worse. Let's start with data consistency and integrity. Data consistency means information in your database doesn't conflict with itself. Data integrity means information is accurate, complete, and follows the rules you have set. In combination, these two terms are about defining appropriate data types, constraints, and relationships among entities to ensure that data remains consistent across different tables, data redundancy is minimized, and anomalies are prevented. For example, given two related entities, it's better that they are represented using different tables, and they don't share more columns than the primary/foreign key. Otherwise, you will have redundancy issues as well as insert or update anomalies. Such issues can have real impact on real world. Think about when you order a laptop online. The confirmation page shows that the price is $1 short of $1,000, but your email receipt says it's actually $1,199. Issues with data consistency and integrity can instantly break trust and causes confusion, even in something as routine as online shopping. The second goal is maintainability and ease of use. Maintainability means your database is easy to update, fix, or expand later without breaking everything. Ease of use means it's simple for developers and analysts to understand, write queries, and get the data they need from your database. In short, a well-designed database should be intuitive to use and easy to maintain by the people who use it, including database administrators, analysts, and developers of the web or mobile applications that are powered by the database. A lot of measures can be taken to increase the maintainability of a database. For example, following a constant naming convention is a small thing to do when you design a database, but it can save a lot of time for people to use it or maintain the database in the future. Imagine that you are a data analyst or database admin, and you have to maintain a database with this issue, where IDs are used inconsistently in the database. For example,
In the product table, it's product underscore ID. In the review table, you have a snake case, that's review ID, where I is capitalized. If developers who use a database have to spend time figuring out whether and how ID or identifiers are used as a primary key column, the database is hardly intuitive to use, let alone easy to maintain. The third goal is about performance and optimization. Performance means your database responds quickly, even when handling a lot of data. Optimization means it's designed in a smart way so that it doesn't waste time or resources when running queries. In short, a well-optimized database should give you the right data fast, whether it's one user or a million. You can take different measures to improve the performance and optimize your database. For example, indexing is a common technique to optimize the database performance. Think about the review table in a database supporting an online store. The data in the review table often needs to be sorted by date because potential customers often want to see the latest review of a product that they are browsing. To speed this sorting process, you can index the date column in the review table. So what's indexing? Think of the data in the review table as a library of books. Indexing is the process of creating an index card catalog that lists every book alphabetically along with its location. When you need to sort, you can use the index card catalog to locate every book and put it in the sorted position. This procedure will speed up the sorting task whenever it's needed. The next goal is about data security. Data security means protecting your data from unauthorized access, leaks, or tampering. Only the right people should see or change the data, and no one else. It's about keeping sensitive information safe, whether it's a user password, medical record, or payment detail. You will need to take different measures to secure your database. For example, if you ever need to store payment method information in your database, you should store only encrypted information. Storing customers' payment method information in plain text is a bad idea. If an evil hacker gains access to the database, they will know everybody's credit card number. And that's exactly what happened with Sony PlayStation in 2011. When the server of PlayStation was hacked, hackers stole personal information from 77 million user accounts. Sony admitted in testimony that part of the credit card data was stored unencrypted in many cases. Failing to secure the database has grave consequences. In this case, the estimated loss was over $170 million, and the entire PlayStation network had to stay offline for 23 days to strengthen its security measures. The last goal is about scalability and flexibility. So scalability means your database can grow, it can handle more users, more data, and more traffic without slowing down or breaking. Flexibility means that your database can adapt when your app or business changes, like adding new features or storing new type of data. A good database design makes it easy to grow and change without starting over from scratch. You can take different measures to enhance the scalability and flexibility of your database design. For example, you can implement a cache mechanism for frequently accessed data, such as the product information in the database of an online store. Caching involves storing frequently accessed data in fast access memory, such as RAM, which can significantly improve database performance and responsiveness, particularly as the data size grows. There are many popular caching mechanisms, such as Redis and Memcached. In this video, you'll learn about the 5 goals database design should strive to achieve. If you find this video helpful, give it a thumb up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deeper into database design using real-world examples to explain the concepts. You can find the link to the book in the first comment. Most database projects fail before the first line of code is ever written. Why? Because the design is rushed, or worse, skipped entirely. and have seen teams spend weeks coding only to discover the foundation was broken from day one. Suddenly, queries are slow, features can't scale. Fixing it means tearing everything down. But it doesn't have to be that way. In this video, I'll walk you through the actual process professionals follow to design reliable, scalable, and maintainable databases before touching a keyboard. We'll break it down step by step, from gathering the right requirements to translating them into a robust data model, to implementing and validating your design with data. The first key step of database design is requirement gathering. Requirement gathering refers to gathering the information about the database in different ways, such as talking to other people who will be involved with or using the database in the future, studying existing databases if there are any, and examining other relevant aspects of information management. To talk to other people who will be involved with or using the database, you need to organize meetings, ask good questions, and have conversations with different groups. Let's use the database of the online store, the Sci-Fi Collective, as an example. The Sci-Fi Collective happens to be a typical business. It has 2 owners, 1 manager, several staff who are responsible for tasks such as data entry and customer service, and 3 others who work on software development. For each group, you will need to prepare tailored interview questions, like these. If you are new to this process, you need to know that the generative AI tools can help a lot with this step. For example, you can ask for some example questions from ChatGPT using a prompt like this. Beyond interview questions, you need to prepare many other things beforehand, such as whether to take notes or record the conversation. If to record the interviews, whether you need to gain permission from the organization, how you want to record the interview, or even where to conduct the interviews. That's everything about the requirement gathering step. Now let's talk about the next step, analysis and design. The analysis and design step involves many tasks. Let's highlight a few important ones, such as identify the goals of the database, identify subjects, characteristics, and relationships. After that, you have data modeling and normalization. Let's go over these key tasks one after another. So we're going to start with goal identification. Undoubtedly, this is the first thing you should be doing based on the information that you gather from the last step, requirement analysis. Every database is created for some specific purpose, whether that purpose is to handle the daily transaction of a business or manage the information of an organization. You need to identify the goal of the database clearly because it will be used to help guide your other decisions down the road. So what would a goal look like? Let's use the same example of the Sci-Fi Collective. If you do the hard work to interview the owner, manager, staff, and software developers, you may summarize the goal of this database as this. The database of the Sci-Fi Collective is to maintain information about products, such as their inventory and reviews, and information about users, such as their payment information and purchases, as well as the transaction information linking users and products. In short, that's a typical database for an online store. So the next task is to identify subjects, characteristics, and relationships. To identify subjects and characteristics from the record of the interview, you can look for nouns in the responses to your questions. How do you differentiate subjects from characteristics? Typically, if you can build a sentence with 2 nouns in which one has or owns the other, the one that is possessed is a characteristic, and the other is the subject. What am I talking about here? Let's use an example to make this a little bit more clear. For example, you can put user and password in the following sentence. A user has a password. In this sentence, the password is possessed by the user, so the password is a characteristic of a user, whereas the user is a subject. You need to perform similar deduction on interview conversations. For example, you might ask the following questions to an IT staff member working for the Sci-Fi Collective.
What are the main tasks or activities you perform that involve data storage or retrieval? The participant may give you a response like this. This response, as you can see, is very detailed. The participant answered this question very well, with a lot of useful details. You can track all the nouns and see whether they can be used in sentences with verbs like has or owns to identify subjects and characteristics. However, in real world, you may need to ask a lot of follow-up questions to solicit such detailed information, and that's why experienced interviewers actually start identifying subjects and characteristics as soon as they start the interview, so that they can track which answer is vague and whether follow-up questions are needed immediately, which will save a lot of time down the road. If the transcript of the interview becomes very long, you may also seek the help from generative AI with a request like this on the left side of the screen that says, "Help me identify the subjects and their corresponding characteristics from the transcript of the interview." However, you can't blindly trust AI to do this job perfectly. You will need to double-check and make possibly a lot of small or big revisions to the work of AI. If this task is carried out accordingly, you will at least be able to summarize 2 subjects and 4 characteristics from this snippet of the interview. The 2 subjects are user and author. User has 2 characteristics, account and a payment method, because you can put them in sentences where verbs are either has or owns. Similarly, author also has 2 characteristics, product information and total price. If you do all the hard work required by this task, you will be able to identify these many subjects and their characteristics for the database of the Sci-Fi Collective. You will also be able to identify the following relationships, represented as a bunch of sentences. By relationship, I mean the connection between 2 different subjects, and characteristics don't really play a role here. For example, we know that user and author are 2 different subjects, and their relationship is summarized here in the first item. A user can make multiple authors. An author can be made by only one user. With this information, you will be able to actually engage with data modeling. So data modeling aims to create a conceptual design that shows how the parts of a database fit together and relate to each other. The conceptual design is typically represented visually as an entity relationship diagram, or short for ER diagram. For example, the ER diagram of the Sci-Fi Collective database may look like this. I know that this diagram on the screen contains symbols and syntax that you don't understand yet. They will be covered in detail in the future videos. When an ER diagram is drafted, the next task is typically normalization. So what's normalization? Normalization is about breaking down a table representing more than one entities into smaller tables. For example, someone designed a table product_review to hold data of both products and their reviews. You know that storing information about more than one entity in the same table can lead to redundancy and anomalies. You could fix this bad design by breaking it into 2 different tables, product and review. So this is a snapshot of normalization. Well, the details of normalization are more nuanced, and this concept has a set of clear defined theorems that can guide your actions, which we will cover in the future. Now, you have some basic understanding of what needs to be done and the second key step. Let's move to the next and the last step. The implementation/integration and testing step involves building and validating the database based on the blueprint you made in the design and analysis step. At this step, you will convert your ER model to SQL code that creates the corresponding database and tables. After that, you will populate the database with sample data to test 3 aspects of the database, including functionality. You need to check whether the database performs the expected tasks correctly, such as creating, updating, and deleting data entries. The performance. You need to check how well the database handles a large amount of data or heavy use. Then, the last one is security. You need to verify that the database has appropriate security measures in place to protect sensitive information such as passwords or payment methods. Based on the testing result, you may need to revise your design or fix bugs that you have identified. In case if you ever wonder where the test data can come from, it can either come from your client, the person or the people you are designing the database for, or you can easily simulate such data with the help from generative AI. For example, you may derive an ER diagram from the analysis and design step like this. You can ask generative AI to help you generate sample data for your targeted database system. You can even make sure that the sample data is already in a series of insert commands that's ready to use. This is a task that generative AI excels at. In this video, we went through the 3 key steps in designing a database, including requirement gathering, analysis and design, and implementation/integration and testing. If you find this video helpful, give it a thumb up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deeper into database design using real-world examples to explain the concepts. You'll find the link to the book in the first comment. Most people think database design starts with tables, but it doesn't. It starts with messy real-world ideas, like students, email, or course. And here's where beginners go wrong. They can't tell what should be a table, what should be a column, or what should be ignored entirely. In this video, I'll show you how to turn vague ideas into clean and structured database tables so that your design doesn't break later. We'll cover 2 topics, starting with subjects and characteristics, then to entities and attributes. Let's get started. The database design process starts with interviewing relevant people of the organization who's going to use the database, like the stakeholders, software developers, and technical staff. Beyond the interview, you are also going to gather sample data and study the old system if there is any. For example, think about you are designing the database for an online store named the Sci-Fi Collective that is specialized in selling only sci-fi stuff. You will need to design different interview questions to interview different groups of relevant people and record the interview as well. The recorded data allows you to conduct the necessary analysis that identifies key information, the subjects and characteristics. Why do we need to care about subjects and characteristics? Well, valid subjects will ultimately turn into tables in your database design, and valid characteristics will turn into different columns in the corresponding tables. For example, think about a conversation with a software developer from the Sci-Fi Collective, as is presented here. You asked this question: what are the main tasks or activities you perform that involve data storage or retrieval? And get this response from the one that you interviewed. If you analyze this response, you will be able to identify these subjects and characteristics, as is highlighted here on the screen. How is the analysis carried out? The analysis focuses on the nouns that can be used in sentences with a verb like has or owns, like this. If you parse this response, you will get 2 subjects, user and other, as is shown here, and 4 characteristics like account and payment methods associated with the user, and product information and total price associated with the order. This analysis step can be labor-intensive, but it doesn't necessarily involve a whole lot of critical thinking and decision-making, so you may ask a generative AI tool to give you a hand. With a request for ChatGPT like this: I'm doing database design, help me identify the subjects and their corresponding characteristics from the transcript of the interview, and then provide your transcript. The context, I'm doing database design, is kind of important. Without it, ChatGPT may or may not know what you are doing. And one important feature about generative AI tools is that they are terrible at asking clarifying questions.
or say they don't ask any clarifying questions at all. Of course, you still need to evaluate the work from AI and make a lot of revisions and eventually make your final calls. If you do all the hard work required by this task for the Sci-Fi Collective, you will be able to identify this many subjects and their characteristics as are presented here on the screen. With such information, you're ready to start your design. The next topic is entities and attributes, and this is the step where you convert the identified subjects and characteristics to entities and attributes. Wait a second, did I mention that the subjects will be turned into tables and the characteristics will be turned into columns? Yes, I did. But I was not accurate enough. Between a subject and a table, there's a middleman called entity. An entity is a conceptual idea that you deal with during the design process, whereas a table is its corresponding implementation. The same thing can be said between an attribute and a column. So yes, a subject will ultimately be turned into a table, but it needs to be mapped to an entity first. Characteristics will be mapped to attributes before they are implemented as columns. Now, you are on the same page in terms of the terminology. Let's go over the key things in the mapping process. What's on the screen is an example of the mapping process. The user entity and its corresponding characteristics are what we identified for the database of the Sci-Fi Collective. And when you map them to entities/attributes, it will look like this on the right side of the arrow. There are two key things that I wanted to cover. The first is the entity representation. The second is the naming convention. First, how is the entity represented in the ultimate design diagram? By the end of the design and analysis step, you will deliver a design diagram. The representation is relatively straightforward. We use a rectangular box to represent an entity, and separate the entity name and its attribute names using a solid line. The attribute names will be listed one after another in different rows in this box. For example, the mapping between the subject user and its corresponding entity representation looks like this. The entity is represented as a rectangular box, as you can see here. The entity name, user, is separated from its attributes by a solid line. Okay, that's the first point. The second important thing about mapping subjects to entities is the naming convention. Of course, you're free to choose whatever suits you when it comes to name an entity and an attribute, but doing so arbitrarily will be bad for your design, let alone the implementation that comes afterward. Just think about the inconsistent usage of IDs and how much trouble that would introduce to the database admin, software developers who need to build on top of the database, and the analysts who need to extract data from the database. As a result, you are strongly recommended to pick one of the naming conventions and stick to it strictly. The most popular one is the snake case. Camel case and Pascal comes as the second and the third popular options. Whichever you choose, you need to be consistent and stick to it. For example, in this video, we will stick to the snake case from now on. The feature of the snake case is that words are all lowercase letters and separated using underscores. When the snake case is used, the subject of users will be mapped to the user entity as you see here for the Sci-Fi Collective database. Beyond the selection of the use of a consistent naming convention, you also want to pay attention to whether to use singular or plural in the naming. Singular names have their roots in object-oriented programming, and plural names are more natural as table names. I'm not gonna get into the debate on which one is better. Whichever you choose, just be consistent. The inconsistency on something as small as this could easily drive a dozen of software developers crazy. In this video, we will stick to singular names for entities. Next, the upper limit of name length. Many database systems have limits on column name lengths. MariaDB, for example, limits column names to 64 characters. If you have such a column name, you should shorten it. Last, you should make sure that you are not using any of the reserved SQL keywords as names. Some of the common reserved keywords include table, any, data, or order. The list goes on and on. If you want a list of common reserved keywords in SQL, generative AI can help a lot. However, if you want a list of reserved keywords of a specific database system, like MySQL, you need to check its menu instead of relying on generative AI, because the information from generative AI tools may not be fully up to date. Now you know that the reserved keywords need to be avoided. And we happen to have such a subject named order. If we were to stick to this name, we will be using a common reserved SQL keyword. This will lead to many problems, such as syntax errors in SQL query execution and maintainability problems. As a result, we will rename this entity as purchase. So packing up all you need to know about how to map subjects to entities, the 5 subjects of the SciFi Collective database will be turned into 5 entities as is presented here on the screen. In this video, we went through how to convert messy real-world ideas to entities and attributes. If you find this video helpful, consider giving it a thumb up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deeper into database design using real-world examples to explain the concepts. You can find the link to the book in the first comment. Real companies have paid a huge price for not getting this right. In healthcare systems, there have been cases where patient records got accidentally merged simply because names and birthdays were used as keys. But people change their names, they get married, they get divorced, and suddenly, 2 different patients become one record. The UK National Health Service spent hundreds of millions fixing this kind of data integrity disasters because the system couldn't reliably identify who was who, and it all comes down to one thing: how you choose your primary key. In this video, I'll show you exactly what a primary key is and how it's different from candidate keys and super keys, and most importantly, how to pick the right one to avoid these kind of real-world failures. Let's get started with the first topic on keys. Think about you're designing a database for an online store named the SciFi Collective. Based on the gathered requirements of the system and sample data, it derived the following subjects and characteristics and also successfully turned them into a set of entities and attributes like what is shown here on the screen. As you may notice, you used the snake case naming convention and derived 5 entities in total. Each entity has a set of associated attributes. Now, your task is to identify the primary key for each entity. The first thing that you need to know is that each table or say an entity needs a primary key. To expand on this and define primary key explicitly, it's one or more attributes that can be used to identify an individual role. That said, the values of the primary key column are all unique. Otherwise, they can't be used to identify each individual role anymore. Last, a table has only one primary key. That's the full definition of primary keys. Based on the definition of primary keys, we can peek at the process of picking the primary key given a table. There are 2 steps involved. First, we will try to pick the best candidate key as the primary key. If we managed to do that, then the job is done. If not, if there's no good candidate keys available, we will create a new attribute to serve as the primary key. Here, we mentioned something that requires further explanation: the candidate key. So what's a candidate key exactly? A candidate key is the smallest possible combination of attributes that can uniquely identify a row in a table. For example, let's look at the user entity from the SciFi Collective database. From the gathered requirements, you know that the username, email, and a phone number all need to be unique for each user. That said, they have all met the requirements of being candidate keys. Yes, they are all candidate keys of the user entity. What about the combination of the first name and username? It can also uniquely identify each row in the user table. Because username is unique per user, and the combination of the first name and username can do the job too. Does the first name help or contribute to this task of identifying each row uniquely? Not at all. It's all because of the username. So, is this combo a candidate key? No, it's not, because it's not the smallest possible combination of attributes that can do the job. I mean, you can remove the first name attribute, it can still do the same thing perfectly. As a result, it's not a candidate key. Well, the story doesn't really end here for this combo. We call combos of attributes like thus the super key. Same as candidate keys, super keys can also identify each row uniquely in a table. But shame on them, they are not the smallest combination, which means that you can also find a subset of attributes from them to do the same job. As a result, the relationship between super keys, candidate keys, and primary keys can be visualized as what you can see here on the screen. A table may have many super keys. Some of them are candidate keys, and among those candidate keys, there's only one that you would pick as the primary key. That's everything about the definition of primary, candidate, and super keys. Let's get practical about how to pick the right primary key next. Remember, we talked about this. There are two steps in picking the right primary key. First, we try to pick the best candidate key as the primary key. If we manage to do that, the job is done. If not, if there's no good candidate key available, we will create a new attribute to serve as the primary key. Let's focus on the first step for now. Do you remember the user entity? We have identified 3 candidate keys for this entity, including the username, email, and phone number attributes. Once you identify all the candidate keys, you need to pick one as the primary key. To achieve this, you will use a set of standards to help with the decision-making process. Here are some commonly used criteria. The most important one, of course, is whether an attribute contains only unique values, and whether it can be null or not. The minimum requirement for the primary key is that it contains all unique values, and its values cannot be null. Beyond that, the other criteria check whether an attribute is stable or not. By that, I mean whether its values change a lot or not. You also need to consider whether an attribute is simple, short, and familiar to you. If an attribute contains values that are relatively short, it will help speed up the database. Last, sometimes you may care whether the primary key can prevent redundant rows or not. By that, I mean some natural keys can inherently prevent meaningful duplications. And if preventing duplications is important to you, those attributes will be great choices for primary keys. If we apply these criteria to the 3 candidate keys in this example, we will have some results like this. Assuming that the SciFi Collective allows users to register an account without providing phone numbers, it will make phone number attribute allow null values, so it can't be the primary key. Between username and email, it can be a hard decision. If the system allows users to change username in every 14 days, emails would be a better choice. When a primary key is picked, you will need to indicate it clearly in the representation of the entity. For example, one way to do it is to place a key symbol by the primary key attribute, like what you see here on the screen. In the user entity, we placed this key symbol at the very left side of the email attribute, which is picked as the primary key. Let's look at another example, the product table in the SciFi Collective database. Based on the gathered requirements and information, we identified 2 candidate keys for this entity, or say this table. The first is the product code. The second is a combination of product name and manufacturer. We call a combo like this the composite key. Both candidate keys can uniquely identify each row or say a product in this table. The concept of code comes from the universal product code. Each product being shipped and sold around the world has a unique product code. To pick a primary key between the two options, you will use the same criteria that you just saw in the last example. In this case, the product code is a clear winner over the combination of product name and manufacturer. The product code is simpler and shorter, so we can add a key symbol by the left side of the code attribute, like this. So far, we talked about how to pick the best candidate key as the primary key. But it doesn't always work. Sometimes none of the identified candidate keys would work, or there are no candidate keys can be identified at all. Then we go to the second step, which is to create a new attribute to serve as the primary key. Let's look at an example. The review entity from the SciFi Collective database. This entity represents product reviews, and it has two identified attributes, the review text and the review time. Neither of the two attributes can serve as a candidate key. Not even the combination of the two attributes. Think about it. Two persons can submit the same worded reviews at the same time for the same or different products. None of them can identify a product review uniquely. When you apply the criteria for the primary key selection to them, it will become even more obvious. That said, you don't have a good candidate key available in the review table. What do you do in this case? When something like this happens, you will create a new attribute to serve as the primary key. For example, we can create an artificial attribute named review ID to serve as a primary key in the review table. We call this type of artificial primary key the surrogate key. It is a non-meaningful column that can uniquely identify rows in a table, and its values are typically auto-incrementing integers. The automatic increment is handled by the database system. As curious as you are, you may be thinking whether we can do the same thing to every table, forcing every table to use a surrogate key as a primary key. This will save us the effort of thinking. After all, what's so different between using product code and a surrogate key product ID as the primary key for the product table? If you ever used generative AI tools to help you choose primary keys, you will know that such tools strongly prefer to use surrogate keys regardless of the situation. It's worth mentioning that surrogate keys may not be the best design choice. Natural keys have the power to reduce duplications inherently, whereas surrogate keys cannot do that. In this example, as you can see here on the screen, product ID column by itself can identify each row or say each product uniquely, but can't prevent the same product information being entered repeatedly as different rows. To reduce duplications, when surrogate keys are used, you will have to use the help from a unique constraint, which we will cover in the future. That said, in a situation like this, for the product table, the product code as a natural key is certainly a better choice as a primary key than a surrogate key plus a constraint. That said, you should stick to the two given steps to pick the primary key for a table, instead of just using surrogate keys everywhere. If you follow the two steps to pick the right primary keys for each table for the SciFi Collective database, they may turn out like this, with 2 tables using natural keys and 3 tables using surrogate keys as their corresponding primary keys. In this video, we went through the definition of keys and how to pick the right primary key for a table. If you find this video helpful, give it a thumb up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deeper into database design using real-world examples to explain the concepts. You'll find the link to the book in the first comment.
If you have ever used varchar 255 as a data type for as many string columns as possible in your database design, you're not alone. But you might be designing a database that performs 10 times worse than it needs to be. Choosing a string data type is like picking the right box for shipping. Too small, your data gets cut off. Too big, you will waste space and money. In this video, I'll show you how to choose the right string data type for string columns in database design. We will cover 3 most commonly used string data types in this video. Let's get started. So, data type selection. Data type selection is a task that you take on once you have identified all the entities, attributes, and the primary keys for each entity. Imagine that you're working towards designing a database for an online store named the Sci-Fi Collective, and you have identified all the entities, attributes, and the primary keys. Your next step will be to select the right data type for each column. To do this task right, you need to pick up some knowledge about data types first, and you will start with string data types. The most commonly used string data types are these 3 as listed here on the screen: char, varchar, and text. Char is short for character, and varchar is short for variable character. As a data type, char is used to store strings of a fixed length. Varchar is used to store variable length strings with a known length, and text is used to store highly variable strings with unknown length limit. Assuming that you are very familiar with string data types and know all the details beyond what is shown to you so far, the task of data type selection is basically to identify a string attribute and then pick the right string data type for it based on the requirements you gathered. Now, let's look at each of the string data type more closely, starting with char. Char stores strings of a fixed length, as you can see here from this example. If you have a column representing code of states in US, each code will be exactly 2 characters long, and you will use char2 to represent its size. The 2 that is wrapped up in the bracket indicates that this column will occupy exactly 2 bytes. So when should you consider char as a column data type? When the data of a column are all strings of fixed and uniform lengths, like country code, currency code, airport code, or even language code. When you have a column that has this feature, you should think about assigning char as its data type. For example, this is the product table for the Sci-Fi Collective database. The primary key code stores the universal product code of different products being sold by the store, and each code has the exact length of 12 characters. As a result, you can declare its data type as char12, where 12 indicates its fixed length. You will put this data type at the right side of the corresponding column. For another example, the payment method entity represents different payment methods in the Sci-Fi Collective database. For all the credit and debit cards as payment methods, their card number have the same digits, which is 16. Beyond that, their expiration dates all have 4 digits. So it's safe to declare their data types as char and assign char16 to the card number attribute and char4 to the expiry date attribute. As curious as you are, you may wonder if card numbers and expiration dates should be numbers instead of strings. A good rule of thumb is whether you need to perform calculations on those numbers. If not, they had better stay as strings. If you declare their data types as numbers, you may have to deal with many inconveniences, like leading zeros. Another question you may have is why going with varchar, the variable character string, is a bad choice here for attributes like card numbers or product code. Well, varchar 255 certainly would work in this case for all the 3 attributes in both entities. However, if you do so, you risk wasting space and money. On average, char is 20% faster than varchar. Plus, you will waste some extra space by using varchar here, and that would cost you millions of dollars if the database is used in a highly scalable environment
where millions of users are involved. The next string data type you will take a closer look is varchar. Varchar attributes store variable length strings with a maximum length specified. As you can see from this example column, it's named names with some sample data shown up here on the screen. Varchar 30, as the data type for this column, specifies the maximum length of data in this attribute as 30. Each data point comes with a different length, like Bob has a length of 3, and Jigglypuff has a length of 10. If it is actually running a database system, Bob will occupy 4 bytes because varchar needs to store the actual data length in addition to its actual length. The same can be said for Jigglypuff, which will take 11 bytes. So when should you consider using varchar as the data type for some columns? When you need to store variable length text data, but the maximum length is reasonable and easy to estimate. For example, the user entity from the SciFi Collective database has quite a few attributes that can use the help from varchar data types, like email. Different email addresses come with different lengths, but the maximum length of an arbitrary email address is 320 characters, based on the RFC standards. If you don't know that, it's totally fine. This is where generative AI tools can offer a lot of help. The same can be said for common first names. Its length may vary a lot, but it's almost certain to use less than 50 characters. If you don't know that, generative AI tools can offer a lot of help on figuring out the maximum length of varchar data types. So you can declare the data type of email attribute as varchar 320 and the first name attribute as varchar 50. It's worth noting that an accurate max length of varchar can be more important than you think, and you shouldn't assign it arbitrarily. If it is too short, it will cut data off. If it is too big, it will make you waste space and money. Dropbox once saved hundreds of terabytes space by simply re-estimating the maximum length of columns in its database. A change as small as from varchar 1024 to 80 may seem very trivial, but it can have a big impact if you are in a highly scalable environment. A rule of thumb of using varchar is listed here. If the variable data length of a column is smaller than 1000, you should think about varchar. If it goes beyond 1000, you should consider the next string data type that we are going to talk about, which is text. Text attributes store strings of variable lengths, and they almost have no maximum length, like the comment column example that you can see here on the screen. A comment can be very short, just 3 or 2 words, but it can also be something that goes beyond 10 different paragraphs and as long as an article. When should you consider using text as the data type for some columns? When you have large blocks of texts and its maximum length is difficult to estimate. Think about the review entity from the SciFi Collective database. If you ever read some reviews on Amazon, they can be very verbose and long, but it can also be very short as a single word. Its maximum length cannot be easily estimated, so in this case, text is the best choice for its data type. A rule of thumb when it comes to text is when the data of a column may go beyond 1000 characters and its maximum length is hard to know. In such a case, you should consider using text as the data type for that column. In this video, we covered the most commonly used string data types. If you find this video helpful, give it a thumb up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deeper into database design using real-world examples to explain the concepts. You'll find the link to the book in the first comment. Ever stored prices using float in your database? You might be bleeding money, literally. In 1983, the Vancouver Stock Exchange made what seemed to be a harmless decision. They used a floating point number to track their index value.
Every time a stock was added or removed, a tiny rounding error would occur. Harmless, right? Except those tiny errors added up real fast. Within 2 years, their index had mysteriously dropped over 40%. Investors panicked. The exchange had to reset the index to rebuild the trust, all because of a bad choice in how numbers are stored. In this video, we'll break down when to use int, decimal, or float in your database, and why wrong choice can corrupt your data, hurt performance, or cost real money. Let's get started. Imagine that you are working towards designing a database for an online store named the Sci-Fi Collective, and have identified all their entities, attributes, and the primary keys. Your next step is to select the right data type for each column. To do this task right, you need to pick up some knowledge about data types first, and you will start with numeric data types in this video. The most commonly used numeric data types fall into 3 baskets: whole numbers, floating point numbers, and fixed point numbers. Let's look at the whole numbers first. A whole number is simply an integer. It may or may not allow negative values. If negative values are allowed, we call it a signed integer. Otherwise, it is unsigned. There are 4 types of whole numbers that belong to different ranges, like tiny int, which has the smallest range, or big int, which has the biggest range. Each of them could be signed or unsigned. Int is simply the one type that's used most frequently and good for most cases when whole numbers are needed. I have listed the ranges of each type of whole numbers here, signed and unsigned. But don't ever try to memorize them, because it's pointless. If you ever need to know the range, you could rely on the help from generative AI tools. This is a perfect use case of ChatGPT considering how simple the question is. So when should you consider using whole numbers as a data type of some attributes? When you have some actual values where possible computation or calculation would be performed on them, and they can't be fractional. For example, here's an entity that represents product reviews from the Sci-Fi Collective database. Its review ID attribute is a surrogate key, and its data are all auto-increment integers. So we can declare its data type as integer, and place int by its right side in the review entity representation. For another example, the purchase table from the Sci-Fi Collective database, its purchase ID attribute is also a surrogate key that contains auto-increment integers. Additionally, the product quantity attribute also only contains integers. As a result, you can declare the data types of both attributes as integer and place int by the right side of the 2 attributes. The use case of whole numbers is relatively straightforward. Let's move to floating point numbers. So what are floating point numbers? They are decimals that can tolerate some level of approximation. Before we get to discussing what it means by that, we need to be sure that we are on the same page on terms that are used to describe accuracy. Precision and scale. Precision means the number of digits in a decimal. Scale means the number of digits after the decimal point. In combination, the 2 terms, precision and scale, are used to describe how accurate a decimal number is. Now we are on the same page on terms. Let's get back to our discussion. So there are 2 commonly used floating number data types, including float and double. Float numbers all have a fixed data size as 32 bits, or say 4 bytes. Doubles all have a fixed data size as 64 bits, or say 8 bytes. Because of the size difference, they have different accuracy. Float can guarantee about 7 significant digits of precision, while double can guarantee about 15 to 17 significant digits of precision. So, what would be a good use case to assign floating point numbers as a data type for an attribute? When you have an attribute that stores decimal data that can tolerate some level of inaccuracy, such as sensor reading or scientific data. For example, think about when you are designing a database for a GPS tracker application, and there's a table named user location in the database. This table needs to store users' current latitude, longitude, and altitude to pinpoint users' location. Such data are decimals, and all have about 7 digits after the decimal point. Can such data tolerate some level of inaccuracies? Yes. Would float be a good fit? No. Float can only guarantee the precision of about 7 significant digits of precision,
A piece of latitude data has over 7 digits long after its decimal point. If you make its data type as float, your database can have a location error of over 10 meters, making the application useless for navigation or tracking. To account for the required accuracy, you have to use double. Double can guarantee about 15 to 17 significant digits of precision, and it's good enough for GPS data. Now, you know when you should consider floating point numbers as data types, and how to decide between float and double. Let's move to talk about when you shouldn't consider floating point numbers. Remember the Vancouver Stock Exchange. Their choice of using floating point numbers to track their index value can't guarantee the accuracy that's required, which leads to the accumulation of errors and a big disaster. As another example, if you use floating point numbers to handle currency exchange, it will lead to someone getting more or less than they should because of the rounding errors. So, whenever your data demands full accuracy, you shouldn't consider floating point numbers at all. Such a job is for a different data type, known as fixed point numbers. In short, fixed point numbers are exact decimals for precise values that require full accuracy. Remember the terms precision and scale? They are used to define fixed point number data types. The example that you see here on the screen, decimal 6, 4, defines the data type for an attribute. Its precision is 6, and the scale is 4, and it guarantees exact accuracy for numbers with the same precision and scale. To define the data type of an attribute as fixed point numbers, or say decimal, you need to specify the precision and scale. The keyword numeric and decimal are basically the same and can be used interchangeably. So, when do you need to use decimal as the data type for some columns? When you need to store numbers exactly as you define them, down to the right numbers of decimal places. For example, the product table in the SciFi Collective database has two attributes that deal with money, the price and cost attributes, and they require full accuracy. If all products are sold at a price lower than $100,000, you can safely declare them as decimal whose precision is 7 and the scale is 2. Now you know when fixed point numbers should be considered. As curious as you are, you may wonder, when double is a good fit as a data type, whether decimal could do the job as well. Because if you can use decimal, you can make it simple. Everything would be decimal, right? Well, let's revisit the database supporting a GPS tracker application. Can we declare their data type all as decimal 10.8? For the attributes longitude, altitude, and latitude. Well, 10.8 may have the exact accuracy that is needed. However, when double is good enough, you shouldn't really think about decimal. A double data type would mean that all the data in that corresponding column will have uniform length and would run much faster than data in a column whose data type is decimal. Such a decision has nothing to do with whether decimal would work or not. It will work, but it won't be as efficient as double. In this video, we covered the common numeric data types and discussed when they should be used as a data type for different attributes. If you find this video helpful, give it a thumbs up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deeper into database design using real-world examples to explain the concepts. You'll find the link to the book in the first comment. In 2017, United Airlines canceled 6 and delayed hundreds of flights, not because of weather, not because of a strike. Their systems couldn't agree on what time it was. One stored timestamps in coordinated universal time, another in local time, and chaos followed. Poor handling of temporal data isn't a small bug. It can shut down airlines, break systems, and cost millions. In this video, I'll show you how to use different temporal data types the right way in your database design, so your systems don't go off schedule. The most commonly used temporal data types include date time, and timestamp. Date simply is a data type representing calendar dates. A data point of this type can simply be 2025 June 9th. Time as a data type represents the time of a day. A data sample of this type includes the hour, minute, and second. Date time as another data type can be thought as the combination of date and time, because it contains both the calendar date and the time of a day, all in your local time. Timestamp is similar to date time, but the date and time are tied to a specific time zone, like Pacific time zone or Eastern time zone. That's an overview of all the different commonly used temporal data types. Now let's look at each of them closely, starting with date. As you just saw from the overview, date is the data type representing calendar dates, just the year, month, and date without the time of a day. When should you consider using date as the data type for a column? When you only need the calendar dates instead of the time of a day. For example, think about the database of a library that loans books to people. Typically, only the information of dates are tracked by such a database and the system it supports. So date as a data type would be good enough for attributes such as checkout date and return date. That's date. The next commonly used temporal data type is time, which represents the time of a day without calendar date information. When should you consider time as a data type for an attribute? When you only need the time of a day instead of the date. For example, think about the database that supports course scheduling at a university. The start and end time of a class doesn't need to record the calendar date information. Such attributes are typically assigned a time data type. The date time as a data type combines both the calendar date and the time of a day, and it's bound by your local time zone. When should you consider date time as a data type for a column? When you need both date and time, but don't need to deal with the conversion of time between different time zones. For example, the database of hospitals typically use data time as a data type for appointment time, like this. Because medical records shouldn't change based on the server time zone settings, more importantly, you might need to store very old appointments before 1970 or for future appointments. In comparison, the range of date time is much bigger than timestamp. Date time goes from year 1000 to one short of 10,000, whereas timestamp only goes from 1970 to 2038. Judging by the range, you might think that timestamp is much less powerful, but its power doesn't lie in the range. The power of timestamp lies in automatic time zone handling. A data point of timestamp is tied to a specific time zone or the coordinated universal time. Timestamp data can be converted from one time zone to another, which is very useful when you need to support applications used by people across the world. Speaking of that, when should you consider timestamp as a data type for a column? When you need an accurate time, and your application needs to work across different time zones or servers, then you need the help from timestamp. For example, think about the table storing the purchase records from a database that powers an online store. The store sells internationally, which means that its users come from different time zones. To make the purchase time of such users consistent, you can assign timestamp as the data type for the purchase time attribute. That's everything about timestamp data type. In this video, we covered the common temporal data types and discussed when they should be used in database design. If you find this video helpful, give it a thumb up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deeper into database design using real-world examples to explain the concepts. You'll find the link to the book in the first comment. Have you ever stared at a bunch of entities and wondered even how to start connecting them so that you can have an ER diagram? In this video, I'll show you exactly how to start building relationships the right way step by step and clear up the confusion between different notations. We will start by providing an accurate definition for the ultimate goal of database design, a complete entity relationship diagram. So an entity relationship diagram short for ER diagram, is a visual tool that's used to design databases. It shows how different pieces of information relate to each other. What information? Like entities, attributes, and relationships. Entities are the things you want to store information about, like customers, products, or orders. These appear as rectangular boxes in the diagram. Attributes has the specific details about each entity, like a customer's name, email, and a phone number. Attributes are represented in the rectangular boxes of entities, as well as their corresponding data types. Relationships show how entities connect to each other, like customers place orders, or orders contain products. Relationships appear either as diamonds or lines connecting entities depending on which notation you are using. A complete ER diagram may look like this. Well, you can think of it as mapping out all the important pieces of information and connecting them. For example, in an online store's database, it would have customers who place orders, and those orders contain products. The ER diagram would show these connections visually before you actually build the database. The main benefit is that it helps you plan out your database structure clearly before you start building it, making sure that you don't forget important connections or information you need to store. That's everything about the definition of ER diagrams. Let's move to discuss the different types of notations. There are two very popular notations that are used to draw ER diagrams, including the chance notation and crossfoot notation. So chance notation has its origin in a paper published in 1976 by Dr. Chen, hence the name chance notation. It's widely used by database textbooks and taught across different higher education institutions across the world. For example, the textbook Database System Concepts adopts chance notation for all the ER diagrams used in this book. An example of an ER diagram developed using chance notation looks like this, on the right side of the screen. It comes from the book Database System Concepts. Some notable features of chance notation include representing all the relationships between entities using diamond boxes and using underlines to denote primary keys. In comparison, crossfoot notation has its root in a different paper published in the same year by Dr. Everest. Crossfoot notation is used more widely by the industry and practitioners, and it's also used by some database design books, like Grokking Relational Database Design. I'm one of the authors of the book. An example of ER diagram that uses crossfoot notation looks like this, and it comes from the book Grokking Relational Database Design. In this and all future videos of this series, we will stick to crossfoot notation, mostly for the consideration of practicality. I told many students using chance notation in the past, and the very valuable feedback that I got for many times is that the gap between using chance notation for coursework and using crossfoot notation during work is painful to conquer. Crossfoot notation does have some advantages in comparison, such as crossfoot notation is more visually clear and efficient, without the diamond box representing relationships, where the foreign key goes is more self-explanatory. Beyond that, most popular database design tools default to crossfoot, and crossfoot notation is widely used in business and consulting environments. Okay, that's everything about the notation types. Let's move to explore a bit about how you start connecting related entities. Imagine that you are working towards designing a database for an online store named the Sci-Fi Collective, and have identified all the entities, attributes, and the primary keys. Beyond the entities, attributes, you have also extracted a set of relationships from your requirement analysis. The next immediate task you will face is to connect the entities using lines based on the summarized relationships. This step doesn't involve attributes, at least not yet. So we can do something to simplify our representations of entities by hiding the attributes for now. So we only have 6 entities representing user, product, product review, purchase records of users, and payment methods. Additionally, we can make the relationship summary even more succinct. The nouns in every sentence represent entities. If 2 nouns connected by some verbs show up in one sentence, then the 2 entities are likely to be in a relationship. You may go through a few iterations of trial and error when mapping the summary to a diagram because of possible inaccuracies and misinterpretation. Based on the existing information, we can connect every 2 related entities like this. When you generate a draft diagram, you should test every relationship against the information you gathered and the sample data you collected. Also, take the draft diagram to the stakeholders and explain your design rationales to them, because it's likely that you made some mistakes or neglected something critical in your first iteration. For example, the software developers of the Sci-Fi Collective will point out that an online purchase can't be performed without a payment method. Based on the new information, you need to answer this question shown up here on the screen first, before visiting the draft diagram again. Without the payment method information, an online order can't be finished, and the online store can't bill its customer. In other words, each purchase record needs to be mapped to a corresponding payment method. As a result, a relationship between payment method and the purchase makes sense. So you can add a line between payment method and the purchase to make the 2 entities related to each other. This is how you start building relationships among entities. From here, the next step is to figure out the cardinality of each identified relationship. Cardinality describes the number of rows of one table that can be associated with a single row of another table. That's a big topic that we will cover in the next few videos. In this video, we defined ER diagram, covered 2 different types of diagram notations, and get started on building ER diagrams by connecting entities based on the requirement analysis. If you find this video helpful, give it a thumbs up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deep into database design using real-world examples to explain the concepts. You can find the link to the book in the first comment. Can one person have multiple passports? Or can one passport belong to multiple people? The answer lies in the concept called cardinality. In this video, we'll introduce you to this concept and cover the simplest kind of cardinality, which is a one-to-one relationship. Cardinality is an important characteristic of a relationship between 2 entities, describing the number of instances of one entity that can be associated with a single instance of another entity via the relationship. In case if you feel lost about the terminologies, an entity is essentially the same as a table. An entity is a conceptual idea of a real-world object or concept. A table is the implementation of an entity in a database. An instance is essentially the same as a row. An instance is a conceptual idea. When being implemented, it will be a row in its corresponding table. To complete your ER diagram, you need to analyze the information you have collected from the requirement gathering phase, identify the cardinality of each relationship, and update the draft diagram accordingly. For example, without cardinalities, your ER diagram in its early stages may look like this. There are 2 things we need to explain on cardinalities, including direction and representation. Let's start with an example. Think about the database of a banking system. There are two entities representing users and accounts. So you have user and account as the two different entities, and their relationship can be broken down to two directional relationships, summarized using two sentences as is shown here on the screen. Sentence 1 says that a user has 0, 1, or more accounts. Sentence 2 says that an account is associated with one and only one user. Sentence 1 and sentence 2 represent two different directional relationships between user and account. In sentence 1, the direction flows from user to account. In sentence 2, the direction flows from account to user. In short, a sentence that describes a directional relationship from one entity to another has a subject, verb, and object. The direction always flows from the subject to the object. Now you know what direction means. Let's talk about the representation. Given a directional relationship from entity A to entity B, cardinality describes how many instances of B, which a single instance of A, can and has to be associated with. Cardinality is represented by two graphical symbols on the relationship line between A and B. The symbols are used in pairs to represent the cardinalities. The symbol on the inner side represents the minimum instance number of B that a single instance of A needs to be associated with. We call that the minimum cardinality. The symbol on the outer side represents the maximum instance number of B that a single instance of A can be associated with. We call that the maximum cardinality. Both symbols are placed closer to entity B. See, the direction goes from A to B. Yet the two symbols need to be placed closer to B. That's something you want to pay attention to. Just so you know, you can swap the positions of entities A and B, and that will lead to the positions of min and max cardinalities swapped as well. As you can see, when the direction flows from A to B, the two symbols as a combination are always placed closer to B. Individually, the min cardinality is the symbol that's placed closer to A relatively, while the maximum cardinality is always placed closer to B relatively. Beyond that, you saw some symbols on the screen that requires explanation. The individual symbols, like a bar or a crossfoot, all represent quantities. So quantity 0 is represented by a circle. 1 is represented by a bar, and many is represented by the symbol that looks like a crossfoot. In the example on the left side, the min cardinality of the relationship from A to B is 1, and the max cardinality is many. Now you know the basics about the cardinality. We can revisit the example that you saw earlier. The relationship between user and account entities in the database of a banking system. The relationship between the two entities is summarized as two different directional relationships. On one hand, a user has 0, 1, or many accounts. On the other hand, an account is associated with one and only one user. The first sentence defines the relationship from user to account. Since a user can be associated with as few as 0 and as many as unlimited number of accounts, you can tell that the min cardinality is 0 and the max cardinality is many. The second sentence defines the relationship from account to user. Since an account is associated with as few as 1 and as many as one user, both the min and max cardinalities from account to user are 1s. In the end, you are supposed to merge the two directional relationships as one relationship between user and account entities. After the merge, the positions of the two min and max cardinalities of the two directional relationships would be exactly the same as if you draw them separately. As you can see here from the representation on the screen, the max cardinalities are more closer to the entities. In comparison, the min cardinalities stay further from the two entities. That's everything about the two aspects of cardinality, the direction and the representation. With such knowledge, we can put all the relationships you will see in the future into 3 baskets based on their cardinalities, including one-to-one relationships, one-to-many relationships, and many-to-many relationships. Such a classification is all based on the max cardinalities. We will look closely at the one-to-one relationships in this video. In a one-to-one relationship, each instance, or say each row in one entity, is related up to one instance, or say one row in the other entity. One-to-one, I mean the two ones here, refer primarily to the max cardinalities of both directional relationships. The min cardinalities could either be 0 or 1. Generally speaking, one-to-one relationships are rare. But let's see at least one example to make sure that we're on the same page in terms of this relationship. Imagine that you are working towards designing a database for an online store named the Sci-Fi Collective, and have identified 2 entities, user and user address. The extracted relationship between the 2 entities can be summarized as following. A user may not have an address when they first register an account, but a user must have one and only one address before making a purchase. An address is associated with only a single user. Let's go from here and develop the 2 directional relationships one after another. So a user may have 0 to 1 address. Based on this, we can develop the directional relationship from user to user address. The min cardinality is 0 and max cardinality is 1. So you can add the 2 symbols accordingly. Since the direction goes from user to user address, both symbols should be placed closer to user address entity. In contrast, an address is only associated with a single user, which means that both the min and max cardinalities are 1. The relationship goes from user address to user, so you will place a pair of 2 bars closer to user. After that, you will merge the 2 directional relationships into one. This step is relatively easy to do because all the cardinality symbols stay where they are in the directional relationship representation. They just share the same line between user and user address entities. In case if you think we are finished here, we aren't. There is one more step, which is to restore the representations of entities. So far, we have used a simplified representation of the user and user address entities, because we didn't list their attributes. We need to do so in a fully developed ER diagram. As you do that, you also need to place a foreign key in one of the 2 entities. And that's the only way for the entities to know that they are in a relationship when they are implemented as tables. In a one-to-one relationship, the foreign key is placed in the entity that's close to where the 0 min cardinality is. You may also see other sources call this entity the optional site, and the entity close to the min cardinality of 1 as the required site. The foreign key is always placed in the optional site. This choice supports the data entry order and makes sure that you won't end up with a null value for the foreign key. If you ever try to place the foreign key in the required site, its value will need to be null from time to time, because a user is not necessarily associated with any addresses, especially those users who just register new accounts. In other words, when you follow the order of data entry to add a new user first, there is no existing address ID value that can be referenced at all. Null values can create unnecessary problems for your database. As a result, you should always place the foreign key in the optional side. However, as curious as you are, you may wonder what if both mean cardinalities of the two directional relationships are zeros or ones, and what should you do in those cases? If both mean cardinalities are zeros, both sides are optional, and you can place the foreign key in either of the two entities, like this, what you see here on the screen, or this. It's worth noting that when you have such a relationship, the foreign key values have to be null from time to time. As you can see from this example, a user is not necessarily associated with an address, and an address is not necessarily associated with a user. If you have such a relationship, you need to be prepared to deal with null values. That's when both mean cardinalities are 0. What about when both mean cardinalities are ones? Well, two mean cardinalities as ones are good theoretically, but not in practice. If you ever have a one-to-one relationship whose mean cardinalities are both ones, you need to relax one of them from 1 to 0 for the sake of implementation. Let's use an example to demonstrate this point. Think about the relationship between two entities, department and manager. A department has one and only one manager, while a manager works for one and only one department. This is a classical one-to-one relationship. Both the max and min cardinalities of both directional relationships are 1. This representation is theoretically solid, but impossible to implement. When it comes to data entry, which table should you start with? A department? A department needs to be associated with an existing manager, or manager. A manager needs to be associated with an existing department. In other words, this design asks you to essentially place foreign keys in both sides, or say both tables. Such a design is impossible for data entry. If you enter a row into the department table first, there won't be any manager ID values that you can reference. The foreign key constraint that you put in place will cause SQL to complain and reject the data entry. If you switch the order of data entry and try to enter a manager information first, you will face the same problem. To avoid such an issue, you can relax one of the two main cardinalities from 1 to 0 to make implementation possible. For example, you can modify the relationship between department and manager like this. The first sentence will be revised from a department has one and only one manager to a department has 0 or 1 manager. Based on the revision, you can relax the mean cardinality from department to manager from 1 to 0. After that, you have an optional side again, and you can place the foreign key in the optional side. If the two tables are ever represented in an ER diagram, the proper representation will look like this. That's everything about the one-to-one relationship. In this video, we covered the basics of cardinality and explored one-to-one relationships. If you find this video helpful, give it a thumb up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deeper into database design using real-world examples to explain the concepts. You can find the link to the book in the first comment. A customer may place many orders. A teacher may teach many students. But how do we represent this relationship in database design? It all starts with understanding one-to-many relationships. In this video, we'll introduce you to this concept and explores how to identify and represent one-to-many relationships in database design. Before we jump to the one-to-many relationships, I need to refresh your memory on cardinality first. The understanding of cardinality is important to understand one-to-many relationships. But if you are well-versed in this concept, you can skip this chapter and jump to the one-to-many relationships. Cardinality describes the number of instances of one entity that can be associated with a single instance of another entity via the relationship. there are two key points on cardinality. First, a relationship between two entities can be broken down to two different directional relationships when you look at it from the lens of cardinality. For example, think about the relationship between user and account in a database supporting a banking system. This relationship between the two entities are summarized in the two sentences on the screen. A user has 0, 1, or more accounts. An account is associated with one and only one user. The two sentences represent the two different directional relationships. Sentence 1 is about the relationship from user to account, while sentence 2 is about the relationship from account to user. Every relationship can be broken down into two different directional relationships like this. That's the first point. Second, a directional relationship is represented by two symbols of max and min cardinalities. The three individual symbols represent three quantities, include 0, 1, and many. The circle represents 0, the bar represents 1, and the symbol that looks like a crossfoot represents many. Each directional relationship is represented by two symbols as a pair. For example, the first sentence you saw earlier is on the directional relationship from user to account. The two symbols representing cardinalities need to be placed near the account entity. A user can be associated with 0 accounts, so the min cardinality is 0. A user can be associated with as many accounts as possible, so the cardinality is many. The second sentence is on the directional relationship from account to user, and its cardinalities are placed near user entity. Both of the min and max cardinalities are 1. In the end, you are supposed to merge the two directional relationships as one relationship between user and account entities. After they merge, the positions of the two min and max cardinalities would be exactly the same as if you draw them individually. From the lens of cardinality, we can put all the relationships into three baskets, including one-to-one relationships, one-to-many relationships, and many-to-many relationships. We will look closely at one-to-many relationships in this video. In a one-to-many relationship, one directional relationship has the max cardinality of 1, and the other has the max cardinality as many. The 1 and many here primarily refer to the max cardinalities of the two directional relationships. If both min cardinalities are 1s in a given one-to-many relationship, it will create problems for data entry when they are implemented as tables. As you can see from this example on the screen, when it comes to data entry, the two min cardinalities as 1s essentially mean that when you try to add a row of data into table A, it has to be associated with an existing row in table B. And when you try to add a row into table B, it has to be associated with an existing row in table A. The association translates to placing the foreign key in both tables, which will cause SQL to complain. Beyond that, you will also have a lot of null values in the two foreign key columns, as the minimum association requirement can't be met in real world. To avoid such issues, it's typical to relax the min cardinality of the many side from 1 to 0. The one-to-many relationships are the most common relationships that are modeled in database design. Let's look at a few examples. Imagine that you are working towards designing a database for an online store named the Sci-Fi Collective, and have identified two entities, user and review. The extracted relationships between the two entities can be summarized as following. A user can write 0 to many reviews. A review can be written by one and only one user. Let's go from here and develop the two directional relationships one after another. A user can write 0 to many reviews. Based on this, we can develop the directional relationship from user to review. The min cardinality is 0 and the max cardinality is many. So you can add the two symbols accordingly. Since the direction goes from user to review, both symbols should be placed closer to review. In contrast, a review is only associated with a single user, which means that both the min and max cardinalities are 1. This relationship goes from review to user, so you will place the two bars as a pair closer to user. After that, you will merge the two directional relationships into one. This step is relatively easy to do, because all the cardinality symbols stay where they are in the directional relationship representation. They just share the same line between user and user address entity. There is still one more step, which is to explicitly list all the attributes. As you do that, you need to place a foreign key in one of the two entities. And in one-to-many relationships, the foreign key is always placed in the entity that's close to the max cardinality of many. In this example, that's the review entity. So the full representation of this relationship is like what you see here on the screen. The foreign key is in the many side. Email as a foreign key is placed in the review entity. Let's look at another example. For the same database, you have identified and developed two entities, user and purchase. Their relationship is summarized as what you see here on the screen. A user can make multiple purchases. A purchase can be made by only one user. A user may make 0 to many purchases. Based on this, we can develop the directional relationship from user to purchase. The min cardinality is 0 and the max cardinality is many, so you can add the two symbols accordingly. Since the direction goes from user to purchase, both symbols should be placed closer to purchase. In contrast, a purchase is only associated with a single user, which means that both the min and max cardinalities are 1. This relationship goes from purchase to user, so you will place two bars as a pair closer to user. After that, you will merge the two directional relationships into one, like this. Translating this relationship to their full representation, you need to make all the attributes of both entities explicit. Beyond that, you also need to add a foreign key to the many side, which is the purchase entity, like this. Let's see second example. Let's look at another from the same database. The entities payment method and purchase. Their relationships are as follows. A payment method can be associated with many purchases. A purchase is associated with one payment method. It's simply another classical one-to-many relationship. If you follow the same steps to establish the two individual directional relationships and merge them as one, you will have something like this. The next step is to make their attributes explicit and add the foreign key to the many-side entity. However, before you start, you should know that we have already established two relationships among the three entities. I mean, between user, purchase, and a payment method. We have already added two foreign keys into the payment method and purchase entities. This is based on the work we did in the first two examples. Once you establish the one-to-many relationship between payment method and the purchase entities, purchase will have two foreign keys added to it, email and payment ID. That's not the issue, but you may notice that the three entities form like a circular relationship, right? That's the issue. And it can definitely lead to some problems. This is something that we will address in the future when we cover normalization. Regardless of that, you did a great job in picking up everything about one-to-many relationships so far. In this video, we learned everything about the one-to-many relationships in database design. If you find this video helpful, give it a thumb up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design which dives deeper into database design using real-world examples to explain the concepts. You can find the link to the book in the first comment. When it comes to database design, many beginners try to connect two tables directly in a many-to-many relationship, and then wonder why SQL queries don't work. The secret? You need a third table. In this video, we'll show you how to represent many-to-many relationships properly. Before we jump to the many-to-many relationships, I will need to refresh your memory on cardinality first. The understanding of cardinality is important to understand the many-to-many relationships. But if you are well versed in this concept, you can skip this chapter and jump to the many-to-many relationship. Cardinality describes the number of instances of one entity that can be associated with a single instance of another entity via the relationship. There are two key points on cardinality. First, a relationship between two entities can be broken down into two different directional relationships when you look at it from the lens of cardinality. For example, think about the relationship between user and account in a database supporting a bank system. The relationship between the two entities are summarized in the two sentences as you can see on the screen. First, a user has 0, 1, or more accounts. Second, an account is associated with one and only one user. The two sentences represent the two directional relationships. Sentence 1 is about the relationship from user to account, while sentence 2 is about the relationship from account to user. Every relationship can be broken down into two different directional relationships like this. That's the first point. Second, a direct relationship is represented by two symbols of max and min cardinalities. The three individual symbols represent three quantities, include 0, 1, and many. The circle represents 0, the bar represents 1, and the symbol that looks like a crossfoot represents many. Each directional relationship is represented by two symbols. For example, the first sentence you saw earlier is on the directional relationship from user to account. The two symbols representing cardinalities need to be placed near account. A user can be associated with 0 accounts, so the main cardinality is 0. A user can be associated with many accounts as possible, so the max cardinality is many. The second sentence is on the directional relationship from account to user, and its cardinalities are placed near user entity. Both of the min and max cardinalities are 1. In the end, you are supposed to merge the two directional relationship as one relationship between user and account entities. After the merge, the positions of the two min and max cardinalities would be the same as if you draw them separately. From the lens of cardinality, we can put all relationships into three baskets, including the one-to-one relationship, one-to-many relationship, and many-to-many relationship. We will look closely at the many-to-many relationships next. In a many-to-many relationship, the max cardinalities of both directional relationships are many. The many here primarily refers to the max cardinalities of the two directional relationships. In other words, the name many-to-many doesn't concern itself with the min cardinalities. It can be either 0 or 1. However, we don't represent a many-to-many relationship like what you see here on the screen. Then how are many-to-many relationships represented? Think about a real-life many-to-many relationship between authors and books. An author writes one-to-many books, well, not zero-to-many, because a person who hasn't written a book yet is not an author. On the other hand, a book can be written by one-to-many authors. This is a classical many-to-many relationship. However, we don't represent such a relationship like what you see here on the screen. When such a representation is implemented, you will introduce many problems. As a starter, such a design will force each table to have a foreign key of its counterpart, like this. After that, because an author is associated with potentially many books, you are going to store multiple foreign key values in a single book ID field, which violates something we call normalization rules. Normalization is something that's very important for you to design robust database, and we will cover that in future videos. Or the alternative is that you will end up with many redundant rows. Well, what we showed you here is not possible. You can't have several identical primary key values in either table. So basically, this representation that you see here is impossible to implement without any of the issues. Then, how is a many-to-many relationship represented? Let's stick to the same author and book example, and give them both a few attributes. Like this. The author entity, or say the author table, has 3 attributes: author ID, name, and address. The book entity has 3 attributes: book ID, title, and cover. We're gonna skip the data types here for simplicity. To represent this relationship properly, you need to go one step further by making a junction table that contains only the primary keys of the 2 involved entities, author and book. Also, you must convert the many-to-many relationship to 2 one-to-many relationships between the junction table and both entities. As you see here on the screen, the junction table, author book, contains only the primary keys from the author and the book entities. In this junction table, the book ID and author ID attributes together serve as a composite primary key. It's worth noting that the crossfoot always points to the junction table. The author and the book entities become indirectly related via the junction table. That's how a many-to-many relationship is represented. Now, you have 2 one-to-many relationships whose main cardinalities are all ones. This is theoretically okay, but not compatible with the real world, especially data entry. Think about it. When it comes to entering data into the database, the tables, you will start with either the book table or the author table, then move to the junction table. But the main cardinality of 1 requires that there needs to be at least 1 row in the author book table, the junction table, to be referenced when a row of author is added. To address this issue, you need to relax the main cardinality of the many side from 1 to 0. After that, you will no longer face problems in data entry when you implement such a design. To make sure that we're on the same page in terms of the many-to-many relationship, let's look at another example. Imagine that you are working towards designing a database for an online store named the Sci-Fi Collective, and have identified 2 entities, product and purchase. The product table represents the products being sold by the Sci-Fi Collective. Purchase table represents the order records of users. The extracted relationships between the 2 entities can be summarized as following. A purchase can have more than 1 product. A product can show up in multiple purchase records. This is clearly a many-to-many relationship, because the max cardinalities of both directional relationships is many. Note that a product doesn't have to show up in an order, so the mean cardinality from product to purchase is 0. What you see here on the screen is more like an intermediate step before we reach the proper representation. To do this right, we need the help from a junction table, and we are going to turn this into 2 one-to-many relationships between an entity and the junction table. The idea would be like this. Note that the crossfoot always points to the junction table. Beyond that, whatever you have, both the min and max cardinalities of the original 2 directional relationships will be copied and applied to the relationship flowing from the entity to the junction table. When you make all the attributes explicit, they would look like this. The last step is to relax the mean cardinality from purchase to the junction table, so you won't face problems when it comes to implementation and data entry. In this video, we learned everything about the many-to-many relationship. If you find this video helpful, give it a thumb up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deeper into database design using real-world examples to explain the concepts. You can find the link to the book in the first comment. When it comes to database design, do you really need a weak entity? Or you're just mislabeling a regular one? Weak entities are often introduced when you think an entity depends on another, like a dependent relying on an employee. But dependency alone isn't enough. In fact, many so-called weak entities should have been regular entities instead. In this video, I'll walk you through exactly what makes an entity weak, when to use them, and just as importantly, when not to. By the end, you'll know how to model relationships in your ER diagram without misusing weak entities, and how to recognize the rare cases when they actually make sense. Let's start by defining strong and weak entities first. So what are strong and weak entities? Does this have anything to do with cardinality? No. Strong and weak entities are another characteristic of a relationship between two entities, and that's beyond cardinality. This characteristic, strong and weak entities, may come handy for refining ER diagrams. That said, it is up to you to designate two related entities as strong and weak entities when you think it's appropriate. What's a strong entity then? A strong entity is an entity that has its own unique identifier. Usually that's just gonna be a primary key. It doesn't depend on any other entities to exist or to be identified. For example, the purchase entity that represents orders in a database of an online store. It has its own primary key, the purchase ID, to identify each order or each row individually in the table. That sounds like just another regular entity, isn't it? Yes, it is. There's nothing special about a strong entity if you look at it by itself. What's special is the weak entity that relies on the strong entity. So what's a weak entity? A weak entity doesn't have a unique identifier by itself. It depends on a related strong entity so that it can uniquely identify each row in its corresponding table. How, you may wonder? Well, its primary key is typically a composite key, and it's composed of a foreign key from the strong entity, plus one or more attributes of its own. Of course, it doesn't have to be a composite key. In that case, the primary key will simply be the foreign key from the strong entity. For example, we looked at the purchase table representing order records in a database of an online store. It's a strong entity, or say, a regular entity. Its corresponding weak entity is the purchase item entity, representing the information of an individual product that's involved in an order. As an entity, purchase item lacks readily available keys that can uniquely identify each row, so it relies on the help from the foreign key to do the job. The foreign key is the purchase ID, referencing the primary key from the purchase entity. It's both a foreign key as well as the primary key of the purchase item entity. Now you know what a strong and weak entity may look like. Let's move to the key question. When should or shouldn't you consider using a weak entity in your database design? When? If you check out some textbooks or ask such a question to a generative AI tool, you can find some specific conditions, such as when an entity can't uniquely identify rows by its own attributes alone, or it depends on a related entity for identification, yada yada. But as long as you understand how strong and weak entities are defined, Such conditions don't provide much help because they focus on describing the characteristic of weak entities. But the real challenge is to identify a weak entity. My experience in database design and software development told me a rather practical rule of thumb, which is when designating a weak entity makes your database design simpler and less prone to error, then that would be a great use case. Yes, as long as you know how strong and weak entities are defined, it's up to you to designate some regular entities as a weak entity. There are no such a thing as a natural weak entity because nearly all the entities you design or encounter are simply regular entities, or say strong entities by default. For example, think about two entities from a database supporting movie theater. One represents movie and the other represents tickets. They are in a one-to-many relationship, and both are regular entities. Ticket uses a composite key as its primary key, composed of seat number, room number, and time. And its movie ID attribute in the ticket entity is a foreign key referencing the primary key from the movie table. Does the existence of the ticket rely on the movie? Yes or no? Or you're not sure. If I ask you twice, you may feel less certain about it because without movies, there shouldn't be any tickets being sold by the movie theater. If you really buy that, you can convert ticket from a regular entity or say a strong entity to a weak one. Like this. All it takes is to add movie ID as a part of the composite key in ticket. And the proper representation of a strong weak entity relationship needs to use a dotted line, as you can see here on the screen. So movie ID is a foreign key indeed, but it's also a part of the composite key that serves as a primary key in the ticket entity. Do you feel that this representation is more complex? Certainly yes. Unnecessarily complex database design is terrible because it leads to more complex queries and may require more space and data structure. And it's gonna be less efficient because it's not gonna be something that can be easily understood by human beings either. Unnecessarily complex design is something we should try to avoid, and the decision is yours whether to designate a regular entity as a weak one. In this case, if I were you, I will stick to the version when both movie and ticket are strong and regular entities. Why? It's simpler and easy to understand, friendly to both database systems and other human beings that you need to work with on the same database. Does ticket really rely on movie? That's a good philosophical question, but in database design, the answer doesn't need to be a yes. That said, we also learned something else that we didn't intend to cover, which is that a weak entity can always be converted to a strong entity if you want to. Just like what you saw from the movie and ticket example, all it takes is to stop using the foreign key as a part of the primary key in the weak entity, and convert the line that connects the two entities to be a solid one. Now, let's reinforce this idea by going through a few more nuanced examples. Imagine that you are working on designing a database for an online store named the Sci-Fi Collective, and you have identified all the entities, attributes, relationships. Beyond that, you have also identified the cardinalities of each relationship. Now, it's a good time to think about if there are any regular entities that you want to convert to weak entities. For simplicity and readability, I will hide out the attributes. So you have 7 tables or say 7 entities that's easier to read. User represents user of the platform or say the online store. Each user has an address and possibly many payment methods. Product represents products being sold by the online store. Review represents product reviews from users. Purchase represents all the orders put by the users. Product purchase is a junction table between purchase and product because the two entities, I mean purchase and product, are in a many-to-many relationship. If you just think about whether one entity relies on another in real world, you could potentially identify this many entities as your candidates for weak entities. But should you convert them? The answer is likely no for most of them. For example, the review table sits between user and product and has two foreign keys, one from user, the other from product. This design is solid. If you are stubborn on the reliance of review on user and product entities, you can potentially change review to a weak entity, which will ask you to add email and code as a part of its jumbo composite key. And you need to change the lines connecting the three entities to dotted lines. This change doesn't help anyone, and it complicates things. It makes the design harder to understand and makes the database less efficient, because a bigger primary key requires a bigger storage and a data structure to work. It can also slow queries because they need to be indexed. If you don't know what indexing is, don't worry, we will cover it in future videos, so this is a bad example anyway. The original design is much better. You may wonder if there are any cases in which converting a regular entity to a weak entity helps. Makes the database design simpler and less prone to errors. The answer is yes, but it doesn't occur often. Let's look at a relationship between user and user address of the same online store, the Sci-Fi Collective. This is the original design between the user and user address entities. Okay? A user can have up to one address. The user address entity uses a surrogate key as its primary key, and has a foreign key which references the primary key of user. Now, you can ask yourself the philosophical question: does the user address rely on the user for existence? The answer can certainly be yes. If you agree and convert the user address entity to a weak entity, it will look like this. Now, the user address entity no longer needs the help from the surrogate key. All it takes to identify each address is the email of an user. Remember, they are in a one-to-one relationship, so email as an attribute can identify each address uniquely. It's both the foreign key and the primary key of the user address entity. When you put the two designs side by side, you can tell that the strong and weak entity, in this case, is certainly better, because it eliminates the usage of a surrogate key, and it doesn't add any burdens on understanding such a relationship or database system that's gonna host such a database. In this case, I would argue that the strong and weak entity design makes sense. In this video, we covered what makes an entity weak, when to use such entities, and when not to. If you find this video helpful, give it a thumb up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Cracking Relational Database Design, which dives deep into database design using real-world examples to explain the concepts. You can find the link to the book in the first comment. Have you ever seen a table where one cell holds multiple values, like a list of phone numbers, or product IDs? Or worse, a table with no clear way to identify a single row. These are not small issues. They can break the logic of your queries and ruin your database design. In this video, I'll introduce you to the concept of normalization, and the simplest of all the normal forms, the first normal form. By the end of this video, you'll know what normalization is and how to use the first normal form to help you normalize your database designs. So what's normalization? Normalization is like organizing a library. You are creating a logical system where each book or piece of data has one proper place, making it easier to find and maintain without duplication.
It's a process of organizing a database in a way that minimizes redundancy and dependencies while maximizing data integrity and consistency. In other words, we break the database into smaller, more manageable tables, where each table represents a single entity or concept. The primary goal of normalization is to strengthen data integrity. When do you use, or say start the process of normalization in the database design process? When you draft your first version of the ER diagram, when you successfully identify all the entities, attributes, and relationships based on the requirement analysis, you will have something to normalize. Doing so will help eliminate redundancy, ensures consistency, avoid insert, update, or delete anomalies. Okay? Enough talking about normalization. How do we actually do it? You can use normal forms to guide the normalization process. Normal forms are the rules that can guide you break down a big, messy table into smaller, more manageable tables. There are multiple normal forms, including the first normal form, second normal form, third normal form, and boys called normal form. It can even go up to 4 and 5. Each normal form can address a specific type of problems. The normal forms build on each other with increasingly strict requirements. They form a nested containment relationship, like Russia nesting dolls. To achieve any normal form, you must firstly satisfy all the lower levels. The first normal form is the largest outer doll, and serves as the basic foundation. The second normal form is the next doll inside. It's smaller and more refined, fitting perfectly within the first normal form, but also comes with extra requirements in comparison. The third normal form is the doll nested inside the second normal form, which is even more constrained and organized. It goes on, and you get the idea. Just as you cannot have an inner doll without all the outer dolls containing it, you cannot have a database in the third normal form without it being automatically satisfying the requirements from the second normal form and the first normal form. In this video, we will focus on the largest outer doll, the simplest normal form. A table, or say an entity, is in the first normal form if it meets these criteria. First, in this table, each column needs to contain values of the same data type. Second, each row needs to be unique. Third, each cell in the table needs to contain exactly one value. Let's go over these criteria one after another to make sure that we are on the same page. The first criteria is very clear. Each column needs to have a specific and only one data type. Imagine that you are tasked to design a database for an online store named the Sci-Fi Collective. As long as you go through every step that is required, such as identifying entities, attributes, their data types, and all the relationships, it is very hard for your tables not to meet this criteria. Remember, a complete ER diagram requires every column to have a data type, which means that each column will contain values of the same data types that you designate. Secondly, a table that is in first normal form needs to make sure that each row is unique. In other words, the table needs to have a primary key that can uniquely identify each row in the table. Similar as the first criteria that asked for data types for each column, as long as you did every step to put together your ER diagram, each table should have a primary key, which may come in various forms, such as a natural key like an email, or product code, or a composite key, or even a surrogate key. If you need to refresh your memory on how to pick the optimal primary key for a table, you can refer to the linked video in the description. The third criteria of the first normal form is worth some good explanation. It says that every cell of the table contains exactly one value. Or you may see this being phrased as there are no multi-valued columns. What does the one value mean? Or say, what does the multi-value columns mean? Let's look at an example that violates this criteria, like this one. This table is supposed to represent what courses students take in a database supporting a course management system. The troublesome column that violates this criteria is the course column. As you can see here on the screen, each cell in this column holds the values of multiple different courses, and they are separated using commas. For a table to be in the first normal form, each of its cells can contain only one value. Or say that there shouldn't be any multi-valued columns like this course column. To fix such an issue, you need to separate this course table into two different and smaller tables. Specifically, you need to split the multi-valued column into a new table. And in this new table, you will make a separate row for each value that was packed in a single cell in the old representation. So in this case, you will have two tables, one representing students and the other representing the courses they take. In the course table, since you split each multi-valued entry to its own row, it will require a composite key composed of both columns to uniquely identify each row. In summary, a new table that splits each multi-valued cell into its own row is the fix for this type of first normal form violation. However, we are not entirely done here. A question that I got asked a lot by students on this particular point looks like this. Who decides whether something is multi-valued? Many people feel that there's no clear standard when it comes to decide whether a value should be further split into multiple pieces, which would directly impact the determination of multi-valued columns. For example, imagine that you have a customer table in a database supporting an online store. The table has 4 columns: customer ID, first name, last name, and email address. Some sample data in this table may look like this. Now let's focus on the email column. As you know, each email address is composed of 2 parts, the username and the domain name. Should you consider an email address as multiple values, and further splitting them into 2 different columns, one representing the username part, while the other representing the domain name part, like what you see here on the screen? Of course, to avoid redundancy and anomalies, the next step is to move the 2 columns into a new table, right? But let's hold on there and think again about this. Should you do this or not? Here's a rule of thumb that works very well. Whether something is multi-valued or not shouldn't really be up to your whim, but up to how users see it. Before you make such a move, you should ask yourself whether users care about splitting email addresses into multiple pieces. By users, I mean the users of the application supported by the database, which is the customers of the online store in this case. The answer is likely no, which means that an email address shouldn't be considered multi-valued, and the move to split the email address column into 2 in a new table won't be necessary. And that's how you should think when it comes to decide whether a column is multi-valued or a table cell contains multiple values. Ask yourself how the users of the application supported by the database feel about it. To make sure that we are on the same page, let's look at another example. What you see here on the screen is a receipt example from an online store named the Sci-Fi Collective. Same as our receipts, it contains the detailed information of each product you ordered. Their unit price and quantities, of course. There is also a total price. If someone who designs their database decides to translate the information from a receipt directly to a table, they will have a table like this. They may name it as purchase, in which each row of the table will represent an order from a customer. The logic may sound straightforward, but the issues will appear as soon as you start populating this table with data. As you can see here on the screen, in the product ID column, each cell will contain multiple ID values of different products. The same thing can be said for the product name column. Ask yourself,
would the users of the application supported by the database see multiple product names as multiple pieces of different values? If the answer is affirmative, that means that you have a violation of the multi-value criteria of the first normal form. To fix this issue, you need to move the two problematic columns into a new table and split each entry into multiple rows, so that each cell in this new table will contain a single value. In this split, the new table will represent the itemized product information that is involved in a single order, and the table will contain the information such as the product name, unit price, and quantities. That's how you use the first normal form to guide your normalization of database designs. In this video, we covered the concept of normalization and the simplest normal forms, the first normal form, as well as how to use it to help you normalize database designs. If you find this video helpful, give it a thumb up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deeper into database design using real-world examples to explain the concepts. You can find the link to the book in the first comment. Your table looks fine. It has a primary key. Each column has a data type. And each cell has a single value. But something still feels off. Some columns only depend on a part of the primary key. This issue will lead to all kinds of insert anomaly, update anomaly, and delete anomaly. How do you fix such a design? You need the help from something known as the second normal form. In this video, I'll walk you through a simplified and a full version of the second normal form, and explore how to use the second normal form to guide the process of normalizing database design. By the end, you'll have a good understanding of the second normal form and how to use it for normalization. Maybe we'll start with a simplified version of the second normal form first. A few words on normal forms first, in case if you need to refresh your memory. So what are normal forms? Normal forms are the rules that can guide you break down a messy big table into smaller, more manageable tables. There are multiple normal forms, including the first normal form, second normal form, and the third normal form, and it can go on. Each normal form addresses specific types of problems. The normal forms build on each other with increasingly strict requirements. They form a nested containment relationship. To achieve any normal form, you must firstly satisfy all the lower levels. For example, for a table to satisfy the requirement of the second normal form, it has to satisfy all the requirements of the first normal form in the first place. The first normal form checks the fundamental stuff, such as whether a table has a primary key or multi-valued columns, and whether each column has a data type. If you need to learn more about the first normal form, you can find the link of a video dedicated to the first normal form in the description. In this video, we will focus on what problems the second normal form aims to address. Remember, we're on our journey to understand a simplified version of the second normal form for now. If a table is in the second normal form, then every non-key column should depend on the whole primary key, not just a part of it. There are two terms that require some clarification. First, by non-key column, I mean the columns that are not the primary key or a part of the primary key, in case the primary key is a composite key that has more than one columns. Second, depends on here refers to functional dependency. To fully understand it, we need to introduce you the concept of functional dependency. What's functional dependency? It's about one piece of data determining another. For example, suppose you have a function called power that takes an input and returns its square value. Given any value of x, the output of power x is completely determined by x. You can also say that the result of applying the power function to a number functionally depends on that number.
when the same concept is applied to columns in the same table, you will have something like this. If you know the value of column A, you can figure out the value of column B every time with no exceptions. For example, think about a table representing employees, and the table has only two columns, employee ID and employee name. Employee ID is the primary key of this table. Given a value of the employee ID, you can always figure out the corresponding employee name. We can say that employee ID functionally determines the employee name in this table and express this dependency relationship using an arrow that goes from employee ID to employee name. You may also see the same relationship expressed as employee name functionally depends on employee ID. Okay? That's everything about functional dependency. And we are going to use it to deepen our understanding of the second normal form. And let's go back to the second normal form now. Beyond asking the table to be in the first normal form, the simplified version only has one criteria, which is about non-key columns functionally depending on the primary key. And it's worth emphasizing that it has to be the whole primary key, not a part of it. Let's focus on this criteria and explore what a violation of this criteria may look like, and how to fix it. For example, think about an enrollment table representing which course a student enrolls in a database supporting a course management system. The enrollment table uses a composite key as its primary key, and it is composed of two columns, student ID and course ID. Beyond the primary key, the enrollment table has three more columns, student name, course name, and grade. When the table is populated with data, it may look like this. On the first look, the design of this table is fine, until you find out that the table contains three functional dependencies, and two of them only uses a part of the primary key. The first functional dependency is where student ID functionally determines student name. As you can imagine, the course ID doesn't help with that at all. The second functional dependency is where the course ID functionally determines the course name. Similarly, student ID won't help much with determining a course name. We typically refer to these two functional dependencies as partial dependency, because the determinant in the two relationships is simply a part of the primary key. Only the last functional dependency uses the primary key as a determinant. The primary key, student ID plus course ID, in combination, determines the grade. How do you fix a violation of the second normal form like this? In general, you need to move any columns that depend on only a part of the primary key to a new table, along with the part of the key. The part of the key will become the new table's primary key. So in this case, you need to move student name plus student ID to a new table. And we can call this new table student, and its primary key is student ID. The same thing can be said for the course name plus course ID. We can call this new table course, and its primary key is course ID. What would happen to the old enrollment table? In general, you will leave behind only the columns that truly depend on the entire original composite primary key. For the columns that meet both conditions, they will be kept in both the newly created table and the old table, such as the student ID column and the course ID column. That's how you fix a violation of the second normal form. Now you have a good understanding of the simplified version of the second normal form. It's time for us to learn about the full version, or say the real thing. In the simplified version, we laser focused on the relationship between a non-key column and a part of the primary key. But the full version is actually a bit broader. Beyond the primary key, it also cares about any candidate keys in the same table. The full version of the second normal form states that no non-key columns depend on a proper subset of any candidate key. In other words, in a table that doesn't violate the full version of the second normal form, you shouldn't be able to find any non-key column that partially depends on the primary key or any other candidate keys. To make sure that we're on the same page, I want to explain what it means by a proper subset. It means a smaller group that's completely contained within a large group, and it can never be as large as a large group. Let's look at an example when this concept is being applied to keys. Think about the enrollment table in the database of a course management system. It's using a composite key as its primary key, so 3 columns in combination, including student ID, course code, and term code. They make the primary key. Okay? A proper subset of this key can be composed of any columns from the 3 columns, but the total number of the columns of this set has to be smaller than 3. For example, the combination of course code and term code makes a proper subset of the primary key, or student ID and term code. Whatever you do, in order to make a proper subset, it can't be the same as the original primary key. Okay? So, by a proper subset of any candidate keys, the full version of the second normal form is still talking about partial dependency, but in a more accurate way. Now you know the definition of the full version of the second normal form. Let's compare the simplified version to the full version, so that you can have a robust understanding of the second normal form and appreciate the fine-grained difference between the two versions. Let's look at this employee project table, which represents the projects employees are engaged with in a company. The table uses a composite key as its primary key, which is composed of 2 columns, employee ID and project ID. Beyond that, it has 3 more columns, employee social security number, or short for employee SSN, project name, and credit score. In addition to the primary key, the table has another candidate key, the combination of employee SSN and project ID. The table has 2 functional dependencies. The first one is about the primary key functionally determining 3 columns, including employee SSN, project name, and project budget. The second functional dependency is about employee SSN, functionally determining the column of credit score. In case if you think the design of this table is ridiculous, it is indeed. However, a reasonable and authentic design that can differentiate the simplified and the full version of the second normal form doesn't really exist. So bear with me on this. Okay, let's continue. Does this table violate the criteria of the simplified version of the second normal form? Then you need to ask yourself, do you have a partial dependency on the primary key? Nope. So it's perfectly valid in the eyes of the simplified version of the second normal form. However, does the table violate the criteria of the full version of the second normal form? Employee SSN is a part of a candidate key. Yet, it functionally determines another column, which is the credit score. That said, you do have a violation, and the table is not in the second normal form. Okay? How do you fix the issue? In the same way as you would fix a violation of the simplified version of the second normal form. You will move the columns that depend on only a part of a candidate key to a new table, and keep only those columns that fully depend on a key in the original table. In this case, you will move employee SSN and credit score to a new table, and employee SSN, the determinant, will become the new primary key in this table. Beyond that, you will also keep the columns in the original table, the columns that are not partially dependent on any candidate keys. In our case, there's one column, employee SSN, that meets the requirement of both conditions, so it's gonna be kept in both tables. Okay? In real world, most violation of the second normal form is on the simplified version. The violation that happens to a candidate key that doesn't serve as a primary key is very rare, but being able to understand their fine-grained difference is still important theoretically. If you get it now, you can pat yourself on the shoulder. Good job. In this video, we covered a simplified and a full version of the second normal form and how to use them to guide your normalization of database design. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deeper into database design using real-world examples to explain the concepts. You can find the link to the book in the first comment. Imagine this. You updated a student's major name in one row in a table, but forgot to change it in other three. Now your data is inconsistent, and worse, your reports are wrong. This happens when your table has transitive dependencies. In this video, you'll learn how the third normal form can be used to address issues like this in your database design, and why it matters in real-world situations. Let's get started. A few words on normal forms first, in case if you need to refresh your memory. So what are normal forms? Normal forms are the rules that can guide you break down messy big tables into smaller and more organized tables. There are multiple normal forms, including the first normal form, second normal form, and a third one, and it can go on and on. Each normal form addresses specific types of problems. And normal forms build on each other with increasingly strict requirements. They form a nested containment relationship. To achieve any normal form, you must first satisfy all the lower levels. For example, for a table to satisfy the requirements of the third normal form, it has to satisfy all the requirements of the first normal form and the second normal form in the first place. The first normal form checks the fundamental stuff, such as whether a table has a primary key or multi-valued columns and whether each column has a data type. The second normal form is about dealing with partial dependencies of any keys. If you need to learn more about the first normal form or the second normal form, you can find the links of videos dedicated to the two normal forms in the description. In this video, we will focus on the problems that the third normal form aims to address. Remember, we are on our journey to understand a simplified version of the third normal form for now. Based on the definition of the simplified version, if a table is in the third normal form, then no non-key columns in this table can be transitively dependent on the primary key. There are two terms here that require some clarification. First, by non-key column, I mean the columns that are not the primary key or a part of the primary key in case if the primary key is a composite one that has more than one columns. Second, transitively dependent. Before we get to this term, let's make sure that we are on the same page in terms of what a dependency means first. In the context of columns of a table, functional dependency means that if you know the value of column A, you can always figure out the value of column B every time without exception. In such a case, you can say that column A functionally determines column B. Or you can also say that column B functionally depends on column A. For example, think about a table representing employees, and the table has only two columns, employee ID and employee name. Employee ID is the primary key of the table. Given a value of the employee ID, you can always figure out the corresponding employee name. We can see that employee ID functionally determines the employee name, and express this dependency relationship using an arrow that goes from employee ID to employee name. You may also see the same relationship expressed as employee name functionally depends on employee ID. Okay? Now to transitive dependency. It means a non-key column is functionally dependent on another non-key column, which in turn is functionally dependent on a key in the table.
Now you know what transitive dependency is. Let's go back to the issues the third normal form aims to address. I mean the simplified version of the third normal form. If a table contains transitive dependency, it means trouble. It means that the table violates the third normal form and needs to be fixed. For example, think about a table representing employees of a company. It has 4 columns and uses a surrogate key, employee ID, as the primary key. The table contains 2 functional dependencies. The first is about the primary key functionally determining 2 other columns, including employee name and department ID. The second functional dependency is about department ID functionally determining department name. Based on such information, you can tell that there's a transitive dependency, which department name is functionally determined by department ID, which in turn is determined by employee ID. Before we talk about how to fix such an issue, I want you to know what issues transitive dependencies may cause. Think about when the table is populated with data. There would be a lot of redundancies since many employees will belong to the same department, which means that the same department ID values and department name values are repeated in many different rows. Beyond that, if you ever try to update a department name, you will need to make sure to update every row that contains the old value. If you ever forget to do that, there will be data inconsistency. In short, it will cause data redundancy and all kinds of update and delete anomalies. Now you know what the problem is, let's talk about how to fix the issue. You need to move the columns in the transitive dependencies to a different table, and the determinant will become the primary key in the new table. In this example, that's the department table. Additionally, you will keep all the columns that are directly dependent on the primary key in the old table. So the employee table will have 3 columns after the update. Notice that the department ID will show up in both tables in our fix. That's because it perfectly meets the 2 conditions. I mean, it's directly dependent on the primary key in the employee table, as well as it was involved in the transitive dependency. That's why it ended up showing in both of the 2 tables after we fixed this design flaw. Beyond a bad design inherent to a single table, a violation of the third normal form can also be caused by 3 tables in a circular relationship. For example, think about 3 tables from a database supporting an online store. So the tables are user, payment methods, and purchase. The user table represents users of the store. Payment methods represent users' different payment methods that are used for ordering stuff online. And the purchase table represents the order records from users. Between each pair of the 2 tables, it's a one-to-many relationship. However, that also leads to putting 2 foreign keys, payment ID and email, into the purchase table. Payment ID is the primary key in the payment method table. Email is the primary key in the user table. However, we know that the primary key in a table functionally determines all other non-key columns. From the payment method table, we can learn that payment ID determines email. From the purchase table, we have something similar, which is the purchase ID functionally determines payment ID. If we put these 2 relationships together and focus your attention on the purchase table, we will have a transitive dependency like this, in which purchase ID functionally determines payment ID and payment ID also determines email. So, by definition, that's a transitive dependency, even though the purchase ID can also directly determine email in the same table. How do you fix such an issue? When 3 tables present themselves in such a circular relationship, all you need to do is to remove one of the 3 relationships so that the table that suffers from transitive dependency issues will no longer need to. In this case,
you can remove the relationship between user and purchase. In other words, you need to remove the foreign key email from the purchase table as well. The fixed relationship will look like this. With such a fix, you may wonder how the purchase table can be connected to user if there's ever such a need. They can still go through the payment method table. That's everything about the simplified version of the third normal form. Let's move to look at the full version and explore the fine-grained difference between the simplified version and the full version next. In the simplified version, we laser focused on the transitive dependency on the primary key. But the full version is actually a bit broader. Beyond the primary key, it also cares about any candidate keys that are involved in transitive dependencies. The full version of the third normal form states that no non-key columns are transitively dependent on any candidate key. In other words, in a table that doesn't violate the full version of the third normal form, you shouldn't be able to find any non-key column that is transitively dependent on any keys. Now, you know the definition of the full version of the third normal form. Let's compare the simplified version to this full version, so that you can have a robust understanding of the third normal form and appreciate the fine-grained difference between the two versions. Let's look at the enrollment project table, which represents student enrollment at a university. The table uses email address as the primary key. Beyond that, it has three more columns: student ID, name, and GPA. In addition to the primary key, the table has another candidate key, the student ID. The table has three functional dependencies. The first one is about the primary key functionally determining two columns, including student ID and GPA. The second is about student ID as the candidate key functionally determining name and GPA. The third is about the name column functionally determining the GPA column. In case if you think the design of the table is ridiculous, it is indeed ridiculous. However, a reasonable and authentic design that can help differentiate the simplified and the full versions of the third normal form almost doesn't exist. So bear with me on this and let's continue. Does this table violate the criteria of the simplified version of the third normal form? You can ask yourself, do you see any transitive dependency on the primary key? Nope. That said, it's perfectly valid in the eyes of the simplified version of the third normal form. However, does the table violate the criteria of the full version of the third normal form? Student ID as a candidate key functionally determines name, and name in turn functionally determines GPA. That said, you do have a transitive dependency on a candidate key. So the table is not in the third normal form. How do you fix this issue? In the same way as you fix a violation to the simplified version of the third normal form. You need to move the columns in the transitive dependencies to a different table, and the determinant will become the primary key in the new table. In this example, that's the name GPA table. Additionally, you will keep all the columns that are directly dependent on the primary key and any other candidate keys in the old table. So the enrollment table will have three columns after the fix. Notice that the name column will show up in both tables. That's because it perfectly fits both conditions. I mean, it's directly dependent on the primary key as well as was involved in the transitive dependency. That's why it shows up in both tables after we fix this design flaw. I know that the name GPA table looks really ridiculous in real world. You would never put such two columns as one table. But let's just focus on the things at the theoretical level. After all, an example that can do this job, differentiating the two versions, is very elusive. In this video, we covered a simplified and a full version of the third normal form, and how to use them to guide your normalization of database designs. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deeper into database design using real-world examples to explain the concepts. You can find the link to the book in the first comment. Imagine that you have followed all the rules, designed a database that meets all the requirements of the third normal form, but it still breaks. That's exactly what happened to Raymond Boyce in the 1970s, which led to the development of the Boyce code normal form, short for BCNF. In this video, we are going to introduce you to a new normal form, the Boyce code normal form. Yet, this video isn't just about BCNF. It's also about how one of the most elegant theories in databases turned out to have a subtle flaw, and how a young researcher caught it. Before we get to the drama, let's quickly recall what the third normal form is trying to prevent. For a table to be in the third normal form, it needs to be in the first and the second normal forms first. What the third normal form specifically requires is that no non-key columns can be transitively dependent on any candidate keys. For example, a violation of the third normal form may look like this. When a non-key column functionally depends on another non-key column, and ultimately on some key, like this. To fix a table that violates the requirements of the third normal form, you need to move the columns in the transitive dependencies to a different table, and the determinant will become the primary key in the new table. Additionally, you will keep all the columns that are directly dependent on the primary key in the old table. There would be typically a column that meets both of the two conditions, and it got to be placed in both tables, like what you see here in the example on the screen. The third normal form was developed by Edgar Codd in 1970s. His work laid the foundation for nearly all modern database systems, for which he won a Turing Award. The development of the third normal form was detailed in his paper titled The Rational Model of Data for Large Shared Data Banks, published in the 1970s. After the paper was published, for 4 years, no one examined or challenged whether the third normal form definition was sufficiently rigorous. In 1974, a young scientist named Raymond Boyce was working through a database design example and noticed that something odd. When two candidate keys shared a column, third normal form doesn't always protect you for update or delete anomalies it is supposed to address. For example, think about a table named Teacher Course. It's a messed up design, of course, and probably won't make much sense to the real world. But it is still useful enough theoretically. The table has two candidate keys, and both are composite keys. The first one uses teacher ID and course ID, while the second one uses course ID and room. The functional dependency in the table is between two columns. Course ID depends on room. This design is perfectly valid in the eyes of the third normal form, as all the columns belong to some candidate keys. So there's no non-key columns, thus no transitive dependencies. However, if the table is populated, and when you ever try to perform an update, such as updating the room where CS101 is told, you need to remember to find all the rows where course ID is CS101 and then update all their rooms. Otherwise, you will have an update anomaly. Remember, the functional dependency between course ID and room asked you to do so. So the third normal form is not strict enough, especially the focus on non-key columns. Theoretically speaking, you can have some rogue columns that are part of a key and still gives you the trouble of transitive dependencies. Actually, it doesn't have to be a transitive dependency either. As you saw in this example,
when a part of a key is functionally dependent on a part of another key, it is already bad enough to give you an update or delete an anomaly. To address such an issue, Edgar and Raymond worked together to develop the boys called normal form. It requires a table to be in the third normal form first. Beyond that, it also requires that every determinant in a table to be a superkey, but nothing else. The new normal form successfully fixed the loophole discovered by Raymond. If a table is not in BCNF, it would fix its design by splitting it to two more smaller tables based on the violating functional dependency. In the example that we visited, it's the course ID determining room that violates the BCNF, so we split them to two different tables, and make the determinant the primary key in the new table. The original table should only keep those columns that are determined by superkeys. Since course ID meets both conditions, it's gonna be kept in both tables. That said, I need to confess that BCNF is rarely used in real world because it's very hard to find a table that violates only BCNF but not the third normal form. However, BCNF is still valuable to database theories and the foundation of the field. The best part of this story is not just about BCNF or the loophole of the third normal form. It's about people. Edgar initially resisted the idea that his definition of the third normal form was incomplete, but eventually embraced the correction. And when the two successfully developed a new normal form that fixed the issue, Raymond's name came first in its name. BCNF may be rare in practice, but it represents something important, the pursuit of completeness, even when the flaw is rare. In this video, we started from the tiny loophole of the third normal form and explored how it was discovered and fixed, and ultimately led to the boys called normal form. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deeper into database design using real-world examples to explain the concepts. You can find the link to the book in the first comment. Think primary key and unique constraints are basically the same thing. They are not, and the misunderstanding can quietly break your database design. Sure, both enforce uniqueness, but only one of them does something extra, something critical. And choosing the wrong one might mean your app would allow duplicated emails, break foreign key references, or silently fail when you try to insert new rows. In this video, we'll cover two types of constraints, the primary key and the unique constraints, as well as break down the real differences between the two with clear examples and recommended practices. By the end of this video, you'll know how and when to apply both of the two constraints when it comes to implementing your database design. Let's get started by defining constraints first. What are constraints? Constraints are SQL rules that are being applied to columns in a table to ensure data accuracy and reliability. When you need to maintain the data integrity of your database or need to enforce some business rules, constraints will be your friend. A good way to think about constraints is to think about traffic rules for a city. Just as traffic lights, stop signs, and speed limits ensure cars move safely and orderly through intersections, constraints ensure data flows properly through your database tables. Let's look at some specific examples in terms of what constraints can do. Think about the database supporting an online store named the Sci-Fi Collective. In this database, there's a table representing users of the online store. There are a bunch of columns in this table that can't tolerate null values, such as username, password, or the first and the last name of the user. This is something constraints can help with. Beyond that, in the same table, there are two columns that must contain unique values, the username column and the phone number columns. This is also something constraints can help enforce. This user table
is related to another table representing payment methods of users. The link between the two tables is the email column in the payment method. Email is a foreign key in this table. Whenever a new row of payment method is inserted into the payment method table, it needs to reference a valid existing user. This is something a foreign key constraint can help ensure. In this video, we'll look at two types of constraints specifically, starting with the primary key constraint. As you know, when it comes to database design, you probably have been told that you need to pick a primary key for every table, and indicate the primary key clearly and explicitly, like what you see here on the screen, or this. When your design of an entity is translated to SQL code for the implementation purpose, the column that you pick as the primary key requires a primary key constraint. The primary key constraint ensures two things. First, it guarantees that no duplicate rows with the same primary key value exists in the same table. Second, it ensures that no row with a null primary key value can be inserted into the table. Without the primary key constraint, your pick of the primary key can't carry out the tasks a primary key is supposed to do. How do you implement a primary key constraint? Let's look at the user table in the database supporting the same online store again. Translating such a design directly to SQL code, ignoring all the other requirements for constraints except for the primary key, you will have something like this. The primary key keyword is placed in the same line as the column that's designated as the primary key. Well, a better approach will be to name the primary key constraint explicitly. This is how you name a constraint, starting with the keyword constraint, then followed by the constraint name of your pick. For every constraint, or every type of constraint that allow you to name it, the way that you approach naming will be the same. After you name the constraint, you will list the primary key keyword again, and you need to wrap up the column in a bracket. If the primary key is a composite key, you will squeeze them all together into the same bracket and separate them using commas, like what you see here on the screen. The purchase product table uses a composite primary key composed of two columns, purchase ID and product code. Why is it better to name a primary key constraint, or any constraints as long as naming is allowed? The name that you pick will make it easier for you to access it and change it in the future if you ever find it necessary. If you don't name a constraint, the database system you use will give it a default name. It's painful to retrieve the default name, and the default name is typically very long and composed of random letters and digits that don't make much sense to human beings. As a matter of fact, the choice of not naming constraints explicitly can be a big inconvenience in the future, and that will slow you down. As a result, it's recommended for you to name every type of constraint, even the primary key constraint. Of course, the caveat is naming of a constraint is allowed, because there are certain constraints that don't allow you to name them at all, like not null or default in some database systems. But that's a different story. The next type of constraint is unique. What does a unique constraint do? Unique constraints ensures that all values in a column or a combination of columns are different. When do you want to use a unique constraint? When you have some non-key columns in a table that should all contain unique values, it can be a simple column or a combination of columns. For example, a single column. Let's look at the user table again. In this table, the username column needs to all have unique values. Translating it to SQL code, it will look like this. We start by naming the constraint. After that, it is followed by the unique keyword, and then the column will be wrapped up in the bracket. If you have a combination of columns that need to have unique values, like the table that you see here, product table comes from the same database supporting the same online store. It's using product code as a primary key. Beyond the primary key, the combination of name and manufacturer of each product needs to be unique. Translating it to SQL code, you will have this. As you can see here, the syntax remains the same. We start by naming this constraint. After that, it is followed by the unique keyword. Then, we use a bracket to wrap up the combination of name and manufacturer columns. That's everything about the unique constraint. Now, let's compare the primary key constraint and a unique constraint to deepen our understanding of both. Let's start by discussing the similarities between the two. Comparatively speaking, the similarities between the two constraints are straightforward. Both of them are used to prevent duplicate rows being inserted into a table. Both use similar data structures to guarantee quick lookup when it comes to checking duplications. Duplications don't only get generated during data insertion. Sometimes it can happen during update. So both of the two constraints will do their job accordingly whenever it's a data insertion or update operation. That's the similarity. Now let's talk about the differences between the two constraints. There are three major differences. The first one is easy to understand. The two constraints serve different goals and happen to have overlap between their functionalities. A primary key needs to be picked deliberately for every table that you design, and it serves as the main identifier for each row in a table. But unique constraints are typically added due to some business requirements. We start our database design by identifying entities, attributes, and primary keys for each entity. But we don't start the design with unique constraints. You get the idea. Second, a table can only have one primary key, but many different unique constraints. That's right. Sometimes you will have several non-key columns that require the help from unique constraints. But no matter what you do, a table can only have one primary key. For example, let's look at the user table again. Beyond the primary key, I mean the email column, there are two non-key columns that require the unique constraints, the username and a phone number. If you think about it, it makes sense as each user should have a different username and a phone number. When you translate such a database design to SQL code, you will have this. As you can see here, two unique constraints are defined on the two corresponding columns. In comparison, no matter what you do, you can only apply one primary key constraint per table. Third, the primary key constraint helps prevent null values, but the unique constraint typically doesn't. In most database systems, a column that has a unique constraint will allow many null values to be inserted, such as MySQL or Postgres. Because a null value is not a real value. It's a representation of something is missing, or say the value is missing, or a column, a field does not have a value at all. For example, if you revisit the user table that we have implemented a few slides ago, and focus your attention on the phone number column, think that the business logic of the online store database that contains this table allows null values for phone numbers. A unique constraint will serve it very well. When users register accounts with this online store initially, they are not asked to provide phone numbers immediately, but they need to eventually if they want to receive text alerts. The phone numbers they provide, however, must be unique per user. That's why a unique constraint serves the phone number column very well in this table. Another question that you need to ask and answer here is a scenario that involves a comparison between surrogate key and a composite key. How is that relevant to the two constraints that we discussed? In some cases, you would have a composite candidate key composed of a few columns.
Regardless if you choose it as the primary key for the table, it has to be unique as a combination, like the example that you see here on the screen. A product table in the database supporting the same online store. The combination of the name and manufacturer columns need to be unique. So the two columns can be designated as the primary key. Or you could go with a surrogate key for the table and add a unique constraint to the two columns as a combination. Both primary keys would work fine, but which one is better from the perspective of database design and performance? A short answer is that surrogate keys are typically preferred in such a scenario. A surrogate key is easier to index and takes less space to build a data structure that prevents duplications. Beyond that, when the table is related to other tables, and when the primary key of the product table needs to be referenced elsewhere in other tables, a surrogate key will be easier to use and more efficient than a complex composite key. That said, if you face a dilemma like this, think about going with a surrogate key. In this video, we covered and compared the primary key and unique constraints. If you find this video helpful, give it a thumb up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deeper into database design using real-world examples to explain concepts. You can find the link to the book in the first comment. Most SQL learners know about foreign keys, but few know about how to fine-tune what happens to a record that's being referenced when you perform a data delete or update. Let's fix that. In this video, we'll cover the foreign key constraint and the referential actions. By the end, you'll have a deeper understanding of how to use foreign key constraint effectively in implementing database designs. In case if your memory on foreign keys become vague, a foreign key can be thought as a link between two related tables. A foreign key is simply one or more columns in a table that reference the primary key of another table. The two tables are of course related. For example, think about the database supporting an online store named the Sci-Fi Collective. There are two tables in this database, and they are related to each other. One table represents products sold by the online store, while the other table represents product reviews. The product table uses the product code as the primary key, and the review table uses review ID as its primary key. The two tables are in a one-to-many relationship. The foreign key is in the many side, or say the review table. That makes the product table the parent table, and the review table the child one in this relationship. The same review table is also related to the user table in the database. User table uses the email column as the primary key. The relationship between user and review is another one-to-many relationship, in which the review table is on the many side. So the foreign key email goes into the review table. That makes the user table the parent one and the review table the child one in this relationship. As you can see, the review table contains two different foreign keys. This is common in database design. How do you translate the design of foreign keys, or say the review table into SQL code when it comes to implementing your database design? The recommended approach is to name the two constraints and define them individually, like this. The keyword constraint allows you to name a constraint. The definition of the foreign key constraint starts with the foreign key keyword. After that, you need to wrap up the target foreign key column in a bracket. After that, you need to specify which primary key is referenced by this foreign key via the references keyword. It will be followed by the related table and its primary key. The primary key goes into another bracket. Does the foreign key constraint do anything? Of course. If you try to insert a new row of review data into the review table, but references a non-existing user,
SQL will complain and stop you from doing that. Similarly, if you are trying to delete a user from the user table, but that user is referenced by several rows in the review table, you will be stopped. Or if you are trying to update the primary key value of a user who is referenced in the review table, you will also be stopped. That's the power of the foreign key constraint. However, that may not be what you truly want to happen when it comes to deleting or updating a row of data in the parent table, like user or product. Sometimes, when we need to delete or update a row in the parent table, we want the referenced row in the child table to be deleted as well. Or sometimes, we want to keep those rows in the child table, but make the referenced foreign key value to be set to null so that data integrity of the tables can still be maintained. Is that something that can be done in SQL? Yes, that's where referential actions come into play. So what are referential actions? Referential actions are about handling what happened to all the related rows in the child table when a referenced row in the parent table is updated or deleted. For example, think about the product and review table. In this relationship, the product table is the parent table, and the review table is the child table. When you need to delete or update the primary key of a row in the product table, but it happens to be referenced by many rows in the review table, you can specify whether such an action is allowed or not, and what should happen to the rows in the review table that references the particular product you want to delete or update. There are 3 types of referential actions that are commonly used, including restrict, cascade, and set null. Let's talk about each of them one after another. Restrict prevents any modifications or deletions of a parent record if dependent child record exists. For example, the database will throw an error if you try to delete a product row who is referenced in the review table. Restrict is the most conservative approach that helps prevent accidental data loss. You may see that I put no action in a bracket right by restrict. Restrict and no actions are actually 2 different types of referential actions, but they behave almost the same. No action also stops any modification or deletion of parent records if dependent child records exist. The only difference between the 2 is timing, which doesn't matter much here. So for simplicity, we will think them as one type of referential actions. When you create a foreign key constraint, either restrict or no action is used by default. That said, as soon as you create a foreign key constraint and don't do anything extra, restrict or no action is already enabled. Of course, you can also choose to be more explicit about it. That requires you to use 2 clauses, onDelete and onUpdate. OnDelete is the clause that defines the referential action type when a parent record is deleted. OnUpdate is the clause that defines the referential action type to use when a parent record is updated. Both need to be followed by some referential action type. Such clauses need to be placed in the definition of your foreign key constraints. That's everything about the most conservative type of referential action. However, it may not be what you want to happen. In some cases, you want your delete or update query to be executed on the parent table, and that requires the help from other types of referential actions. Cascade. If this referential action is chosen, when a record in the parent table is updated or deleted, the corresponding change will automatically propagate to all related records in the child table. For example, if you delete a product, all the referenced reviews are also going to be deleted. This maintains a consistency, but can also result in widespread data loss if not used carefully. If this is what's required by the business logic, you need to specify it accordingly when it comes to defining your foreign key constraint, like this. The cascade should follow the onDelete and onUpdate clauses, and they should be placed in the foreign key constraint definition. Just for the record, onDelete and onUpdate are totally independent, and they don't have to take the same type of referential actions. And everything is up to the business logic. For example, if you want to use Cascade to handle all updates, but don't want delete to happen in the same manner, you can go with Cascade for the onUpdate clause, but restrict for onDelete clause, like this. The third commonly used referential actions is setNull. If this referential action is used, when a parent record is deleted or its key value is updated, the foreign key values in related child records will be set to null. As you can imagine, this would require the foreign key column to allow null values. For example, if setNull is used as the referential action type, when the product record is deleted, any review rows that reference the product record will have their product code value set to null. To use this type of referential actions for delete, setNull should follow the onDelete clause in the corresponding foreign key constraint. As you can see from this example, onUpdate is followed by Cascade, which handles the modification in the parent table differently from the deletion. In this video, we covered what the foreign key constraint is and how referential actions work. If you find this video helpful, give it a thumb up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deep into database design using real-world examples. You'll find the link to the book in the first comment. Most developers think constraints like not null, default, or check are just nice to have, optional at best. But in reality, ignoring them can silently corrupt your database. Let me show you what I mean. Imagine a column that allows null values for a status column. What does a null status even mean? Is it pending, failed, or forgotten? You don't know, and that ambiguity can ripple through your application. Or take check constraints as another example. They are your last line of defense against invalid data. Unless you skip them and let a negative salary number slip into your system. In this video, we'll break down how these three constraints really work and how to use them to make your SQL code safer, smarter, and robust. By the end, you'll know how to use these three constraints effectively to enforce business logics when it comes to translating your database design to SQL code. Let's start with the not null constraint. A null value represents a value that's missing or unknown. It can cause unexpected troubles when you are not aware. For example, when you are trying to do some aggregation calculation, but accidentally involves even a single null value, the result can be null. The not null constraint helps ensure that a column doesn't accept null values in SQL. Whether you are talking about data insertion or update, it doesn't matter. That column that comes with a not null constraint will not accept any null values. The usage of not null constraint is simple. For example, think about a table representing users in a database supporting an online store, which has quite a few numbers of columns that shouldn't accept null values, except for the phone number column. Translating this business logic to SQL code, you will have something like this. As you can see here, the code snippet lists not null constraint in the same line as soon as a column is defined. You may wonder if not null is a constraint, why we don't name them in the same manner as other constraints like the primary key constraint or foreign key constraint. People who design database systems see not null as a fundamental column property, like data type or length. Same as how you don't name the data type of a column, you don't need to name a not null constraint either. As a matter of fact, most database systems don't support naming of not null constraints at all. Beyond that, you may notice that we gave a not null constraint in the primary key column, the email column. Is that really necessary? Technically speaking, it's redundant, because if the primary key constraint is applied to a column, that column will not accept null values. However, this is still a recommended practice, because if you change the primary key constraint in the future, you don't need to worry about where to patch up in terms of the not null constraint. In other words, this small redundancy is future-proof. Last, not every column requires the not null constraints. I'm not talking about the business logic. Sometimes it can come from the requirement of an optional relationship. For example, think about the relationship between customers and automobiles in a database supporting car dealership software. The two entities are in a one-to-many relationship. A customer can correspond to many cars, and the foreign key goes to the many side, or say, in the automobile entity. Yet, both main cardinalities of this relationship are 0, which makes the relationship optional. The implication of such a design is that when a row of automobile data is added, it doesn't have to be associated with a customer at all, which will translate to the foreign key column in the automobile table, allowing null values. In summary, optional relationship, or say two main cardinalities as 0, would translate to foreign key columns that allow null values. In such a case, you need to be careful and shouldn't apply not null constraints to every column without thinking. That's everything about the not null constraint. Let's move to the default constraint now. The default constraint is used to ensure that a column always has a value. The value is either specified by the user or the constraint. Well, it's more often specified by the constraint rather than the user. Let's look at an example. Think about two related tables, purchase and payment method, from a database supporting an online store. The purchase table represents the order records, and the payment method table represents the payment methods used by users. There's one column in the purchase table named purchase time, which is used to record the exact time when a user puts an order online. This is a perfect scenario for you to use the default constraint. Instead of relying solely on the software developers to do the right thing, you can lessen their burden by setting the default value of the purchase time to be the time when a new row of purchase data is added. The syntax of the default constraint is simple. Add the default value to the same line of your column definition and make sure to provide the proper target value, like this. The current timestamp stands for the exact time when a new row is inserted into the table. Additionally, we chose not to name this constraint. It's worth noting that some database systems see default constraints in the same way as not null, as an integral part of a column definition, so they don't support the naming of such a constraint, like MySQL, while some others do. If you're thinking about naming a default constraint, you can start with a simple question to generative AI tools and further look it up in the corresponding database system menu. So when would you find yourself in a situation that needs help from the default constraint? When you have a column that stores timestamp, a numeric column that you might perform aggregation on later, or an optional column that holds placeholder values. The most common scenario is definitely the first one. So let's dive deeper into that by answering two questions. First, does the default constraint replace not null constraint? Remember, we looked at this table. For the purchase time column in the purchase table, we added two constraints, not null and the default. They can't replace each other. The default constraint can't prevent users from adding null values to the corresponding column. So the answer to this question is a no. If you need to prevent null values, the not null constraint is definitely needed. The second question has something to do with the commonly used default values for timestamps. Current timestamp. A common confusion on this is whether current timestamp adopts Coordinated Universal Time or the UTC automatically. Well, the answer to this question has two parts. First, it's safe to say that the current timestamp is widely supported by most database systems, such as MySQL, MariaDB, SQLite, and Postgres. However, when it comes to whether current timestamp adopts UTC or not is a totally different story. In some database systems, like MySQL, current timestamp adopts UTC automatically. So default current timestamp will support auto time zone conversion without any issues. But in some other systems, like Postgres, things are a little bit complicated. Whether current timestamp adopts UTC automatically or not depends on what data type you choose for the corresponding column. There are two different flavors for the data type timestamp. One comes with auto time zone conversion and adopts UTC automatically, which is a timestamp with time zone, while the other does not. If you are dealing with a database supporting users across different time zones, you want to use one. If you are dealing with a database supporting users across different time zones, you want timestamp with time zone. Like this. You need to specify the data type as timestamp with time zone. By doing that, the default current timestamp will do the job as is intended. How to create a column representing the current timestamp and support time zone conversion is one of those things that you want to double check by talking to a generative AI tool and further look things up in the menu of the corresponding database system. That's everything about the default constraint. Let's move to the check constraint now. Check constraints are to some extent more capable and complex in comparison with not null and default constraints. Let's start with a simple question. What does a check constraint do? A check constraint is a rule that specifies a condition for a column so that each row must meet this condition to be considered valid for this column. For example, think about the table representing persons. The table comes with a few columns, like person ID, last name, first name, and age. The valid age number is between 0 and 120. The check constraint can check the validity of age values based on such a rule, and reject any data insertion or update that is considered invalid. When do you need to use check constraints? When you need to enforce business logic, set valid value ranges, or predefined datasets, or validate basic pattern, you can always rely on the help from the check constraints. Let's look at these scenarios one after another. First, enforcing business rules. As you conduct the requirement analysis for database design, you may gather some information about certain columns in an entity. Translating such information to SQL code requires the help from the check constraint. For example, think about a table representing book loans in a database supporting libraries. There are a few columns representing borrow date, due date, and return date of books. The rules that you gathered require that the due date to be later than the borrow date, and the return date to be the same or later than the borrow date. Enforcing such rules requires the help from the check constraint, like this. As you can see here, we start the definition of this constraint by naming it first. After that, we made two rules and concatenated them using the AND logic operator. Both rules are wrapped up in the bracket that follows the check keyword. The first rule says that due date needs to be later than the borrow date, and the second rule says that the return date needs to be the same or later than the borrow date. Such business rules won't get reflected in database design, but if they are enforced during database implementation, they need the help from the check constraint. The second scenario is range validation. When you have some columns that are numeric data, their data may not make much sense when they are not in a certain range. Although requirement analysis may not reveal such information explicitly, a qualified database designer can catch such issues and translate them into constraints. Remember the person table and age column that we visited a few slides ago. The requirement analysis of the database may not contain anything about valid data range of age, but it's not hard to deduce a valid range for human age and translate it to a check constraint, like this. For another example, think about a product table from a database supporting an online store. Its price column can use some help from a check constraint. If the price range is known to you, for example, between 1 cent and 1 cent short of a million, the check constraint may look like this. If the upper range is unknown, it could simply be like this. The next scenario is list validation. Sometimes you have a column whose valid values are limited to a small and predefined set, like transaction status or gender selection. In such a case, a check constraint can prevent invalid data from being added into the database. For example, think about a table representing user address in a database supporting an online store that only operates in US. So only 50 state names and a DC should be considered valid. To make sure invalid data won't be added into a table accidentally like this, you can apply a check constraint to this column, like this. List validation requires the help from the in keyword. The syntax is relatively straightforward. State in that is followed by 51 state names, while the 51 state names are being wrapped up in a bracket. Of course, everything still needs to be wrapped up inside a bracket that follows the check keyword. The next scenario that often requires the help from check constraints is format validation. When it comes to pattern matching or format validation, SQL is not as strong as imperative programming languages, but you can still do many necessary and basic checking so that you can have this last line of defense to lessen the burden on the backend and front-end developers. One caveat about doing format validation using check constraints is the inconsistency across different database systems. Let's look at an example to demonstrate that. Think about the same user address table that we've visited. The data type of postal code is car5, which means a fixed size string. If we wanted to apply a check constraint to further limit it to exactly 5 characters long, the constraint may look like this. You may wonder whether this is redundant because car5 can already handle this task by itself. Indeed, it's unnecessary. But this is one of the few pattern matching syntax that is consistent across different database systems. Specifically, I'm talking about the like keyword. It is followed by 5 underscores that are wrapped up in a single quotation mark. That's how you express 5 characters. Can we go one step further by limiting the characters to be digits only? Yes, we can. But the syntax for that part will vary from one database system to another. For example, in MySQL, it will look like this by taking advantage of regular expression. In Postgres, you need to take a different approach, like what you see here on the screen. I'm not asking you to master format validation here. Instead, I'm asking you to have some awareness that you can do basic format validation in SQL as well, but the syntax varies from one database system to another. It's actually where generative AIs can help quite a lot, as long as your question is explicit about which database system you are dealing with. That's everything about using check constraints for format validation. In this video, we covered 3 constraints that can be handy during database implementation, including not null, default, and check, what they are, and when to use each of them. If you find this video helpful, give it a thumb up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deeper into database design using real-world examples to explain the concepts. You can find the link to the book in the first comment. Databases store the most valuable assets of modern systems: user credentials, financial data, health records, or even internal company secrets. A breach doesn't just hurt your users. It can ruin your company, your reputation, and your legal standing. So how do we keep this information safe in your database? Broadly speaking, we rely on 2 lines of defense: access control that governs who can interact with the data, and encryption that protects what the data looks like if someone does access it. Access control decides who can use your data. Encryption decides whether anyone can understand it. Miss either one, your database will become a toast. In this video, we'll unpack these 2 pillars of database security, access control and encryption, and show you how they work together to protect sensitive data from misuse, leaks, and attacks. Let's start with access control. Access control governs who can do what in a database. It prevents unauthorized users from reading, modifying, or deleting data. There are 3 types of access control that you should be aware of, including discretionary control, mandatory access control, and role-based access control. Discretionary access control is the simplest one, but it only works for a small application or toy project because it doesn't scale very well. This type of access control is about the database admin manually determining who can access the database and what permissions they have. So there's not much to say about it. In contrast, the 2 other types of access control deserve some good explanation. Mandatory access control is about assigning a hierarchical levels of clearance to databases, tables, columns, or even rows. And at the same time, it will assign the same hierarchical levels of clearance to its users. A user can only access some data if his or her assigned clearance level matches or exceeds that of the corresponding data. For example, think that we are running a database of a higher education institution and define 3 clearance levels: public, sensitive, and confidential. We then assign them to different tables in the database. Tables like student and course are assigned the public clearance level, grade is classified as sensitive, and medical is classified as confidential. We would also assign such clearance levels to different users who need to access the database. Only when one's clearance level is the same or higher than the corresponding table, the user can access its data. In short, mandatory access control is about managing and assigning a hierarchical of clearance levels to both users and tables. Mandatory access control is mostly used in government, military, and other high-security environments where protecting classified information is critical. In comparison, role-based access control is about assigning access permissions to roles rather than each individuals. Users are then assigned roles based on their job functions. This simplifies the management by grouping permissions into roles that reflect organization structures. For example, think about that we are running a database for another higher education institution and we define 3 roles, including student, teacher, and admin. We then associate the access permissions to each of the roles, like this. After that, we can assign the roles to different users who need to access the database, like this. As you can see, sometimes a single user can be assigned to multiple different roles. Role-based access control is used almost everywhere outside of a strict military or government settings, especially in business, education, healthcare, and online platforms, because it's much easier to manage the mandatory access control and scales very well in comparison to the discretionary access control. When you use SQL to achieve role-based access control, the syntax varies from one database to another. So here, we will only show you an example in which there's some baseline consistency. After all, SQL standards do define a few of the clauses that are key to access control. Think about an online store named the Sci-Fi Collective. In its database, we need to define 3 roles: users, analysts, and administrators. By users, I mean the ones who are the customers of the Sci-Fi Collective and who shop online. The users have read and write access to a few tables, but they can't delete or update anything. The SQL code of creating the user role may look like this for MySQL or MariaDB. It starts by creating the role using the createRole clause, followed by the name of the role, up to your choice. After that, we grant different access permissions to this role, such as the permissions to view data, insert new data into different tables. Dot notation is used here to concat the database name and the table name. As you can see, the grant to clause is used to achieve this goal. Select means view permissions. Select on Sci-Fi Collective. .product means the view permission on the product table. Insert means the permission to add data. Insert on database name. .purchase means the permission to add data into the purchase table. After these 2 steps, the role of users is created. Whenever you have a new user who should have this role, you will grant it to that user. For the admin role, you will follow the same 3 steps to create the role first, then grant different permissions on different tables to this role. In the end, when you have a new user who should have this role, you will assign the admin role to him or her. One thing worth noting here is that you can combine multiple permissions, such as viewing, adding new data, updating, or deleting data of the same table to this role, and pack them into a single grant to clause. The different permissions are separated using commas. That's everything about access control. Let's move to discuss encryption now. Encryption is about protecting data by converting it into a coded format. So if the data is stolen, it can't be read in plain text at all. The 2 most commonly used encryption approaches include one-way encryption and symmetric encryption. We will look at the 2 types of encryptions one after another, starting with the one-way encryption. One-way encryption, also known as hashing, is a cryptographic process where data is transformed into a fixed size string of characters, which is typically a hash value or hash code. The key characteristic of one-way encryption is that it's designed to be one-way function. It's easy to compute the hash value from the input data, but extremely difficult, or say practically impossible, to reverse the process and obtain the original input data from the hash value. This makes it useful for scenarios where you need to verify data without storing the original data in a readable format. Some of the popular one-way encryption algorithms include bcrypt, PDK-DF2, and SHA-512. To enhance security, a unique salt value, or say a randomly generated string, is often added to each password before hashing. This prevents the attackers from using pre-computed hash tables to crack passwords. Regardless of the varying password lengths, the hashed results always have the same length as some binary data. It's a common and recommended practice to actually encode the hashed byte data into strings and store them using char in your database. Encoded hashes can be printed, logged, copied, and debugged more easily. Plus, encoded strings are safe to include in URLs or JSON because the raw binary data may include null values, controlled characters, or invalid encoding sequences. Let's see an example where one-way encryption is applied and explore its implications for database design. Think about the database of the same online store, the SciFi Collective again. In your first iteration of database design, you developed a table named user to store all the information of the customers. There's a column named password that currently stores passwords without any encryption. Now, with the newly acquired knowledge on encryption, you decided to use bcrypt as a one-way encryption algorithm to encrypt the passwords. Bcrypt generates salt internally and results in a 23-byte binary data after hashing. When you convert the binary data to strings using base 64 encoding, all hashed passwords will be 60 characters long. Since salts are unique to each password, you do need to store them, but bcrypt handles that as well. So all you need to do is to make sure that the password column has enough space to store the strings in the hashed format. Like this. As you can see, the change introduced to the database design is very small, yet critical. It relies on your understanding that passwords cannot be stored in plain text, which encryption algorithms to use, and how that algorithm handles things in its own way. If a different encryption algorithm is used, things could be slightly different. For example, if you decide to use SHA-512 to handle the one-way encryption, things will be slightly different. This encryption algorithm doesn't generate salt internally, but still requires salt for hashing. When passwords of different lengths are hashed using this algorithm, they all end up as 64-byte binary data. When such data is encoded using base 64 as strings, they will all be 88 characters long. Remember, SHA-512 still requires salt for hashing. So the backend server needs to generate salt, use it to encrypt the passwords before ever storing them into databases. Beyond that, since salts are unique to each hashed passwords, you do need to store them just in case you need to repeat the same process in the future for the same given password. You can choose to prepare a separate column named password salt to store the salt as binary data. Or you can follow the lead of bcrypt and concata salt with its corresponding hashed password as a single piece of data, and then encode it as a string. This decision may not be all yours to make because it requires the backend server to cooperate. Regardlessly, such a decision will impact the design of the user table. Now, let's move to talk about the symmetric encryption. Symmetric encryption is like having a single key that both locks and unlocks a box. You use the same secret key to encrypt data when you need to store it into the database, and you use the same key to decrypt the data when you need to read it back. This is different from one-way encryption, or say hashing, where data is scrambled but can never be unscrambled. In contrast, symmetric encryption is reversible, meaning that you can always get your original data back if you have the key, making it ideal for storing sensitive information that you need to retrieve later, like credit card numbers or personal details. Common symmetric encryption algorithms include Advanced Encryption Standard, Triple DES, and Blowfish. Each algorithm has a set of variants. Depending on the key lengths, such as 128 bits or 256 bits, AES has three variants: AES 128, 192, and 256. The key length determines the level of security and the computation power that's required for encryption and decryption. The longer the key is, the higher the security and the computational requirements are. Let's use AES 256 as an example of symmetric encryption and think about its application to the same database that we just visited. As you can imagine, the database needs to store the payment information from its customers. The table for this task is named payment method. When a customer or the user buys anything and takes the option to save the payment information for future use, this table stores the credit card information accordingly, including the card number and expiration date. As it stands now, neither of the two columns are encrypted. In case if you wonder, okay, we are storing the credit card numbers, the expiration date, but why don't we store the CVC numbers too? It's all about following the payment card industry data security standards, which recommends not to store the CVC numbers at all. After all, CVC number is either requested again from users or not necessary when the card is used again for future transaction. Assuming that the first transaction, of course, would through successfully. Based on this standard, card numbers and expiration date can be stored in your own database, but both need to be encrypted. As you know, a card number is 16 characters long, and expiration date is 4 characters long if you skip the slash that separates the month and year numbers. As it stands now, the table fails to encrypt either of the two columns considering their data sizes. If we use AES 256 to encrypt both columns, we need to get on the same page in terms of how AES works first. These algorithms use a 256-bit secret key for encryption and decryption. It operates on blocks of 16 bytes of data. If the input data is not a multiple of 16 bytes, one block will require some padding so that you always have a set of 16-byte blocks. Beyond that, AES uses a 16-byte initialization vector to strengthen encryption. Although the initialization vector is not a secret, it has to be unique per encryption. For example, think about how an expiration date August 2029 is encrypted using AES 256. First, the 4 characters, 0829, need to be padded and encoded as a set of 16-byte blocks of data. After that, it is concatenated with the initialization vector. In the end, the combined string will be encrypted using AES algorithm and encoded as a string. This process will turn both a 16-character long card number and a 4-character long expiration date into 64 characters. In other words, if you intend to encrypt both the card numbers and the expiration dates, you need to increase the data sizes of the two corresponding columns to 64 characters. In addition to that, you will need to store the initialization vectors for both the card numbers and expiration dates, because an initialization vector is unique per encryption. If you were to store the initialization vector separately from the encrypted data, you will need 2 more separate columns that store binary data of 16 bytes. It's typically unnecessary to encode the initialization vectors as strings, so binary data will do. If you don't like this option, you may choose to encode the initialization vectors as strings and concat them to the encrypted data. For example, always at the beginning of the encrypted card numbers and at the beginning of encrypted expiration date. In such a case, the encrypted card number plus initialization vector will be 88 characters long. The same can be said for expiration date column. As you can see, encryption only leads to change as minor as increasing the data size of the target column in a database, but a lot of thinking and understanding goes behind the scene. You may also wonder if the secret that's used for encryption and decryption needs to be stored into the database as well. The answer is no, absolutely no. Each initialization vector is unique per encryption, so they need to be stored and mapped to each encrypted data. However, the key that's used for encryption and decryption remains the same all the time. So it is typically stored in key management services or hardware security modules. Regardlessly, you shouldn't store the key in the same database, because it makes a single point of compromise. If an attacker gains access to your database, they get both the encrypted credit card numbers and the key to decrypt them. This makes the encryption essentially worthless. It's like locking your front door but leaving the key under the doormat. In this video, we covered two different aspects of database security, including access control and encryption. If you find this video helpful, give it a thumb up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Cracking Relational Database Design, which dives deep into the database design using real-world examples to explain the concepts. You'll be able to find a link to the book in the first comment. Have you ever wondered how the web applications you use on a databases can find whatever you need quickly when you perform a searching task, like a shopping app or a movie streaming service? Index is one of the powerful tools that makes this possible. An index is like a book's table of content for your database. It creates a separate, organized lookup structure that points to where the data is actually stored, so the database can find rows quickly without scanning the entire table. Instead of checking every single row to find what you need, the index lets the database jump directly to the right location. However, indexes are not created equal. B-tree indexes help with filtering, sorting, or ordering, but they struggle with natural language search. That's where full-text indexes shine. In this video, we will cover two major types of indexes that are widely used in relational databases that support scalable applications, including the B-tree index and a full-text index. Of course, there are other types of indexes as well, such as clustered index and hash index, but we won't cover them here. In combination, B-tree and full-text indexes cover about 85 to 90% of indexing tasks in typical application development. Many developers work their entire career using primarily B-tree indexes. Full index is common enough in modern apps that is worth knowing. As a result, we will focus our attention only on these two types of indexes. Let's start with the B-tree index. So a B-tree index organizes data in a sorted, tree-like structure with multiple levels. When you create a B-tree index for a column in a table of your database, the database builds this additional B-tree structure and stores it alongside your table data. So it's basically a copy of your indexed columns organized in a tree format, with pointers back to the actual table rows. When data is inserted, updated, or deleted, their corresponding operations will be slightly slower because you need to add data to this B-tree data structure or update or delete data from it. However, an advantage of a B-tree index is how fast it can speed up searching and sorting due to its balanced structure. Every path from top to bottom has the same length, guaranteeing that there would be a consistent and a fast lookup. Typically finding any record in just 3 to 4 steps, even in a table with millions of rows. Let's look at an example of how to create a B-tree index and what that may look like. Think about a table named Movie from a database that supports a movie streaming web app. The table comes with 5 attributes, including movie ID, title, date, rating, and a photo. The rating column stores the average rating from all users. The developers of this app noticed that their users frequently sort movies by their ratings. Since this column is not a primary key,
it doesn't come with an automatically generated index. Oh, by the way, when a column is designated as the primary key in a table, a B-tree index is typically automatically generated for that column in most database systems. It helps speed up potential searching and sorting tasks on the primary key. Since rating is not a primary key, it doesn't come with an automatically generated B-tree index. So to speed up searching or sorting on this column, you need to create an index yourself. To achieve that, all it takes is a simple SQL command. Create index, then it's gonna be followed by the index name, then on the target table, in the bracket that follows the table name, you will include the columns that you want to create an index on. So what does this SQL command do? It leads to the creation of a B-tree data structure using the data from the rating column alongside your table data. When searching or sorting is performed on the rating data from the movie table, the database system will be able to use this B-tree structure to speed up things. Similarly, if you are the database admin of this database and notice that sorting is performed frequently on the date column, it's natural for users to sort movies by release dates so that they can check out the latest movies. Since date is not a primary key either, so you need to create an index on it to speed up the corresponding sorting task. You can do it in the same manner as you create the index on the rating column. So far, you have seen two examples in which index is created on individual columns. What if it involves more than one column? Say the streaming app comes with a set of filters that allow users to filter or sort movies by more than one attributes, like both rating and the release date. If you notice the corresponding query is frequently triggered, then you need to create an index on the combination of the two columns, like this. All it takes is to put both of the two columns in the same bracket and separate them using a comma. Remember, you need the help from B-tree index when you need fast lookups, filtering, sorting on a non-primary key column. You typically don't take preemptive measures on indexing until you know enough about how users use your application. The empirical data is golden because it tells you where searching, filtering, or sorting actually happen frequently. Many developers work their entire career using only the B-tree index, because it is indeed the most important index. Standing alone, it probably accounts for 80 to 85% of indexing tasks in relational databases. B-tree index is great for many things that we mentioned, like fast lookups, filtering, sorting, or range queries on structured data, like numbers, dates, or exact matches. But it doesn't work well when you have to deal with a lot of texts. Imagine that you are building a blog and want users to search for articles containing the word database. With a regular B-tree index, you could only match exact values or use slow pattern matching like this query. This query uses a like clause that scans every row, which is painfully slow on large tables. Speeding up the search in a large amount of text data requires the help from a different type of index, the full text index. A full text index is specifically designed for searching within text content. It works by breaking down your text into individual words. We call them tokens. Then, removing common words like a and the. Then, creating a searchable catalog of where each meaningful word appears. Think of it like the index at the back of the textbook, but for every significant word in your content. What makes full text indexes special is how it builds this data structure to support searching of text. Results of full text index aren't just a match or no match. Full text index can score results by how well they match your search terms, putting the most relevant results first. With the help of full text search, you can search for phrases, handle plural forms, and even find similar words. For example, With the help from full text index, searching running might also find run and runs. Last, full text index makes searching much faster. Instead of scanning entire text columns, full text index lets you instantly find all the rows containing specific words, even across millions of records. Now let's use an example to make further sense of when and how to use the full text index and what that may lead to. Think about the movie table again, but this time it comes with a small modification, which is an extra column named description. This column stores the descriptive information of each movie, so it's all text of course, and each row would probably be very long for this target column. If the streaming app of this database supports users to search for movies by typing keywords or anything into a search bar, and primarily matches the input against the movie description, it is only natural that we speed up searching by creating a full text index on the description column. The syntax of creating a full text index varies a lot from one database system to another, so here we will only quickly show you one example that works with Postgres, and focus on what structure is actually created instead. To add a full text index on the description column using Postgres, you need to add an extra column that conforms to a special data structure, and then create an index on that newly created column. So what exactly is generated when a full text index is created? Think about a movie table with 3 rows, and each row contains a description for the corresponding movie. When a full text index is created on this table, it will generate a structure that looks like this. As you can see, this structure stores the mapping from each word to the corresponding movie. You can think this as flipping the original data, or say inverting the original data, which makes searching extremely fast. You can directly look up each searching term and then get back the matching movies instantly, rather than scanning through every movie's description. You may also notice that some common words like and the are filtered out in this inverted index structure. So in a sense, we only kept the meaningful words. This structure is the reason why full text index can speed up searching tasks in texts. In this video, we covered 2 major types of indexing in relational databases, including B-tree index and full text index. If you find this video helpful, give it a thumb up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deeper into database design using real-world examples to explain concepts. You can find the link to the book in the first comment. We spent so much time learning how to normalize databases, remove redundancies, and split table apart so that we can avoid anomalies. But here's the twist. Sometimes we put redundancies back on purpose. Sounds backward, right? Why would we undo what we just worked so hard to achieve? Think of a normalized database like a clean modular circuit. Every component has one job, but sometimes performance demands a shortcut while connecting distant parts directly. That shortcut saves time, but makes the system more fragile. Denormalization is that shortcut in database design. Imagine a dashboard that joins 5 tables to display a report. It's perfectly normalized, but every query takes seconds. Your users don't care about perfect design. They care about speed. Denormalization is one of the ways that we trade a little data purity for performance. In this video, we'll see what denormalization really means, why it's sometimes necessary, and how to do it responsibly. Let's start by properly defining denormalization first. Denormalization is a last-ditch database optimization technique that intentionally introduces some redundancy to a database to improve query performance.
It typically involves two steps. The first step is to identify queries that are used frequently and require joining more than two tables. The identification process requires you to observe how users use your database and gain empirical data first. The second step is to decide whether and how to duplicate some columns in the identified tables so that it can reduce the number of tables that are required to achieve the same result. Let's illustrate this via some examples. Think about a music app like Spotify. You design its database and you are responsible for optimizing it now. One thing that you noticed is that the query that retrieves top songs of famous artists are executed frequently. Yet, famous artists have typically issued many different albums, and songs are associated with album table instead of artist table in the database. That said, this query always needs to join three tables together in order to retrieve top songs from famous artists. Like what you have seen here on the screen, two one-to-many relationships, and a cumbersome SQL query that joins all the three tables you saw. Now you have completed the first step in denormalization. You have identified the query that is frequently used and requires joining more than two tables, and you have found solid evidence that this query takes a bit longer than what users expect for a very basic task. After trying all different optimization techniques, you realize that none of them works very well, so you decided to apply denormalization to address this issue. We already know that the only way to associate an artist to a song is via the album table. To reduce this middleman table, you can build a relationship between artist table and song table directly. The link between the two tables allows you to bypass the album table whenever you need to find the top songs from a famous artist, which will simplify the SQL query. Of course, the old query on the left side needs to join three tables, but now you just can join two tables to achieve the same result at a faster speed. Sounds awesome, right? Such a change doesn't come without a cost. If you focus your attention on the album table, you can tell that it's in a classical one-to-many relationship with artist table. And the foreign key, artist ID, is in the album table. Since the primary key in a table functionally determines all other attributes, we have this functional dependency. From album ID to artist ID, or say album ID functionally determines artist ID, because album ID is the primary key in the album table, and artist ID is not a primary key, as a foreign key is functionally determined by the primary key. Similarly, if you focus your attention on the song table now, it's in two one-to-many relationships with both the artist table and the album table, and both the foreign keys are placed in the song table, including album ID and artist ID. Since the primary key in a table functionally determines all other attributes, we have this functional dependency that goes from song ID to album ID, or say the song ID functionally determines album ID. If you put the two identified functional dependencies side by side, you can clearly see that they would form a transitive dependency like this, which violates the third normal form. Now, you have completed the second step in denormalization, and perhaps have a better understanding of why it's named denormalization, because this change will lead to a violation of normal forms. That's the cost of increased speed and a simplified SQL query. To make sure that we are on the same page, let's look at another example. Think about a database that supports an online shopping store that you design and manage. After a few months of operation, you noticed that this query that joins three tables together is performed frequently. The three tables include user, payment methods, and purchases. As users view their order history, they will keep triggering the query that joins users and purchase table. Yet the two tables are not directly related to each other. To join the two tables, you have to go through a middleman, which is the payment method table. As time goes, you realize that this query is triggered so frequently that it warrants some optimization. That said, you have completed the first step in denormalization. You have identified the query that is frequently used and require joining more than two tables, and you have found evidence that this query takes longer than what users normally expect for a basic task. After trying all different optimization techniques, you realize that none of them works very well, so you decided to apply denormalization to address this issue. To reduce the number of tables that need to be joined, you can add a direct relationship between user and purchase tables. By doing so, you can bypass the payment method table to complete the same task. As you can see, this change will lead you to join two tables instead of three tables to achieve the same result. The updated SQL query is much more simplified in comparison. Of course, the newly gained efficiency and simplicity has some cost. If you focus your attention on the payment method table, it's in a classical one-to-many relationship with user table, and the foreign key is placed in the payment method table. We know that the primary key functionally determines all other attributes, including the foreign key. So from payment method table, we can deduce this functional dependency that goes from payment ID to email, or say payment ID functionally determines email. Now, if you focus your attention on the purchase table, you can see that it's in two one-to-many relationships with both payment method and user tables. And it contains two foreign keys, including payment ID and email. Since the primary key determines all other attributes in a table, we would have this functional dependency that goes from purchase ID to payment ID. If you put these two functional dependencies side by side, you can tell that they can clearly be chained up to form a transitive dependency, like this, which is in violation of the third normal form. Now, you have completed the second step in denormalization, and I've gone through two examples. It's time for us to discuss the best practice on denormalization. Denormalization may sound tempting, but you want to be careful and never misuse it. For example, you don't want to denormalize unless you have measured a real performance problem and tried other approaches first. For another example, if your tables are updated often, like inventory, balances, or user profiles, redundant fields will quickly fall out of sync. In such cases, denormalization can lead to disastrous results. Think about when you need to duplicate a customer's address in multiple tables. As addresses are updated, when your customers move, their data will become a nightmare. Or when your database has a relatively small size, drawing on small or indexed tables are usually very fast, even if multiple tables are involved. In such a case, denormalization gives no measurable benefits. Or if you work in a corporate environment in which multiple teams or systems write to the same tables, denormalization would complicate coordination and increase the risk of inconsistency. Now, you may think that I have cautioned you against denormalization and wonder what other techniques you should try first. Let's talk about them. First, you certainly want to start with indexing the columns that are frequently used for sorting, ordering, and filtering. Next, based on indexing, you want to rewrite your queries to use better join order, window functions, or aggregations. This often brings huge gain without schema change. Beyond indexing and query optimization, you also want to try caching. Application-level cache, like Redis, or memcached can help reduce repeated read load. Or even better, you can keep your database design normalized and only denormalize it in cache. If all these techniques fail and you still urgently need more efficiency, then you move to denormalization. If you have to denormalize, you want to document redundancies explicitly in your README file, and work with your backend developers to use triggers to propagate changes automatically when the source data changes. You also want to run consistency checks to detect divergence between redundant copies and verify that performance improvement would justify the added maintenance complexity. In this video, we covered what denormalization is, used 2 examples to explain its consequences and trade-offs, and discussed the best practice on denormalization. If you find this video helpful, give it a thumb up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deeper into database design using real-world examples to explain the concepts. You can find the link to the book in the first comment.